Take a moment to look at the space around you. Not at the objects, but at the gaps in between. For most of history, we had a simple word for that space: nothing. It was seen as a true emptiness, a silent background against which the universe played out. For a very long time, this was not a guess, but a core idea in science. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The vacuum was the definition of absence, a passive stage for stars and planets. But as our understanding grew, a new picture began to emerge. A quiet suggestion that this emptiness was not empty at all. That hidden in the void was something active, something fundamental. This is a journey into that idea. Not a myth or a thought experiment, but a real property of our universe, revealed by physics. It is the story of how we learned that the silent backdrop of existence is, in fact, filled with a constant, invisible hum. And that what we have always called nothing may be the foundation of everything. To understand just how different the quantum view is, it helps to go back to the world of classical physics. The world of Isaac Newton, where the universe seemed to operate like a predictable machine. In this view, a vacuum was a simple concept. It was the complete absence of things. Imagine a sealed box, shielded from all light and heat. If you could pump out every atom, classical physics said that what remained was absolute nothing. A true void, with no energy, no temperature, and no properties. Our intuition agrees with this. An empty room feels empty. The idea had ancient roots. The Greek philosopher Democritus imagined atoms moving through such a void. Aristotle disagreed, believing that nature would always rush to fill any emptiness. But by the 17th century, experiments by scientists like Evangelista Torricelli showed that a vacuum could be made in a laboratory. The space at the top of his mercury tube was the closest anyone had come to perfect emptiness. This classical vacuum was the accepted idea for hundreds of years. It was the zero point against which everything else was measured. In Einstein's theory of general relativity, a perfect classical vacuum would have zero energy and zero momentum. It was a neat, orderly concept. But it was also incomplete. At the start of the 20th century, a new science was developing, one that did not see the world in such clear-cut terms. That science, quantum mechanics, would gently suggest that nothing was a far more complicated idea. The shift from classical to quantum physics was a quiet one at first, but it changed everything. And nowhere was the change more surprising than in the concept of empty space. The passive void of the old physics was slowly replaced by something far stranger: the quantum vacuum. The first hint of this came from one of the most foundational ideas in modern science, Werner Heisenberg's uncertainty principle. In 1927, Heisenberg realized there was a fundamental limit to what we can know about the universe on its smallest scales. The more precisely you know where a particle is, for example, the less precisely you can know its momentum. This was not a flaw in our tools. It was a basic property of reality, a kind of built-in softness. A different version of this principle applies to energy and time. It says you can never know the exact energy of a system for an impossibly short moment. There is always some uncertainty. For very brief moments, the energy in any given space can fluctuate. And this principle applies even to a perfect vacuum. According to quantum mechanics, even a space with no matter or radiation cannot have an energy of precisely zero. If it did, that certainty would violate the principle. Instead, the vacuum rests at its lowest possible energy state, something called zero-point energy. This energy is not zero. It is a small, but very real, minimum. It is like the surface of a deep ocean. From far away, it looks perfectly flat. But up close, you see it is always covered in tiny, constant ripples. The quantum vacuum has a similar quality. It is the ground state of the universe, but it is always fluctuating with a small amount of energy. This fluctuating energy has a curious effect. Quantum field theory tells us that the universe is made of invisible fields, one for each type of particle. A particle is just a small vibration in its field. In the vacuum, these fields are still present, and because of the uncertainty principle, they are always jittering. These tiny jitters can borrow just enough energy from the vacuum to briefly create a pair of particles, one of matter and one of antimatter. These are called virtual particles. They appear, exist for a moment too short to measure directly, and then vanish, returning the energy they borrowed. This process is happening constantly, everywhere. The empty space between you and this screen is filled with a quiet, ceaseless murmur of these fleeting particles. The quantum vacuum is not an emptiness. It is the lowest energy state of all the fields that make up our universe, a sea of constant fluctuations. And we have found ways to prove that it is real. The idea of a vacuum filled with fleeting particles can sound like a mathematical abstraction. For a long time, many thought it was just a tool for calculations. But science works by observation, and the reality of the quantum vacuum was eventually confirmed by a quiet and elegant experiment. In 1948, the Dutch physicist Hendrik Casimir was studying subtle forces between molecules. In the process, he made a remarkable theoretical prediction. Imagine taking two perfectly smooth, uncharged metal plates and placing them parallel in a vacuum, extremely close together. From a classical perspective, nothing should happen. There is no charge, and gravity at this scale is negligible. But Casimir understood that the quantum vacuum would have an effect. Outside the plates, virtual particles of all possible wavelengths can appear and disappear. Between the plates, however, the space is restricted. Only virtual particles with wavelengths that fit neatly into that tiny gap can form. This means there are slightly fewer virtual particles between the plates than there are outside them. This small imbalance creates a difference in pressure. The particles outside push inward slightly more than the particles inside push outward. The result is a tiny, but measurable, force pressing the two plates together. A force born from nothing but the structure of the vacuum itself. For decades, this was only a prediction. The force was thought to be too small to measure. But in 1997, experiments led by Steve Lamoureux, and later refined by others, measured the Casimir force with great precision. The prediction was correct. The force was real. It was proof that empty space could exert a physical push. This is not the only evidence. We see the effects of zero-point energy elsewhere. It is the reason liquid helium will not freeze solid at normal pressure, no matter how cold it gets. The constant, subtle jiggling of its ground state energy prevents its atoms from settling into a fixed, solid state. And very recently, in early 2026, scientists at the relativistic heavy ion collider found something that seems to connect our world directly to the vacuum. When smashing particles together, they observed that newly created particles, called lambda and antilambda pairs, showed a striking property. When they emerged close to one another, their spins were perfectly aligned, a kind of shared orientation. This alignment diminished as the distance between them grew. This behavior is thought to be a memory of their origin as a virtual pair in the quantum vacuum, a trace of their brief, entangled existence in the void. It offers a subtle window into how real matter emerges from these fleeting fluctuations. Other experiments explore these ideas through analogy. In January 2024, one team created a model of vacuum decay in a lab, using a supercooled gas to watch how bubbles of a more stable state could form within a less stable one. While not a direct observation of the cosmic vacuum changing, it allows us to test the mathematics of these theories in a controlled setting. The evidence, taken together, paints a clear picture. The vacuum is not a tranquil void. It has a physical structure, and that structure has consequences. We have gently set aside the classical idea of nothing, and found that the void seems to be alive with a quiet energy. But this is only the start of the story. The fact that empty space has its own energy is not just a curious detail. It has implications that stretch to the scale of the entire universe. If this kind of calm exploration of physics helps you think, consider liking the video and subscribing to the channel. In the next part, we will move from the very small to the very large, to see how this energy of nothing may be shaping the future of our cosmos. So, we have seen that empty space has a small, baseline energy. It's a fascinating property of quantum mechanics, but it is easy to see it as a minor effect, a tiny force pushing two plates together. How could that matter on the scale of the universe? It turns out it may matter more than anything else. This quiet energy of the void is now thought to be the reason for one of the largest cosmic mysteries we have ever faced, the accelerating expansion of the universe. To understand this, we need to look back to Albert Einstein. In 1915, when he developed his theory of general relativity, the equations suggested something that seemed wrong at the time. They implied that the universe should be collapsing under its own gravity. The accepted view then was that the universe was static and eternal. To make his equations fit this view, Einstein added a mathematical term to them, which he called the cosmological constant. He imagined it as a kind of energy inherent to space itself, an outward push that would perfectly balance gravity's inward pull. A few years later, in 1929, the astronomer Edwin Hubble discovered that the universe was not static at all, it was expanding. The galaxies were all moving away from each other. Einstein realized his addition was not needed and famously called it his greatest blunder. For most of the 20th century, the cosmological constant was mostly seen as a historical footnote. But in 1998, our understanding shifted again. Two teams of astronomers were observing distant supernovae, hoping to measure how much the universe's expansion was slowing down due to gravity. They found the opposite. The expansion was not slowing down. It was speeding up. Something was pushing space apart, faster and faster. Suddenly, Einstein's blunder seemed like a necessary idea again. Scientists needed some kind of repulsive energy spread throughout space to explain what they were seeing. And the quantum vacuum provided a candidate. The idea is that this vacuum energy has a strange quality. It exerts a negative pressure. In general relativity, pressure itself can curve spacetime. While normal pressure adds to gravity's pull, negative pressure creates a repulsive effect. It pushes. So the current picture is this. The zero-point energy of the quantum vacuum acts like a cosmological constant. It gives every part of space a tiny, persistent, outward push. In the early universe, when matter was dense, gravity was stronger and slowed the expansion down. But as the universe expanded, the matter thinned out, and the pull of gravity between galaxies weakened. The vacuum energy, however, is a property of space itself. Its density seems to be constant. As more space comes into being, more of this energy appears. After billions of years, a point was reached where the repulsive push of the ever-growing vacuum energy became stronger than the weakening pull of gravity. From that point on, the expansion began to accelerate. That is the universe we live in now, one being pushed apart by the energy of empty space. This mysterious force is now called dark energy, and the leading explanation is that it is the energy of the quantum vacuum. This would mean that around 68% of everything in the universe is made of this energy of nothing. All the stars, planets, and galaxies we see make up less than 5%. We are like foam on the surface of a deep and hidden ocean. But this elegant picture carries with it a deep and quiet puzzle. It is perhaps the single greatest mystery in all of physics. We have a story that seems to fit together. Quantum mechanics suggests the vacuum has energy. General relativity suggests this energy would cause cosmic expansion to accelerate. And astronomers observe this acceleration. The small scale seems to explain the large scale. It feels like a moment of true understanding. Except for one very large problem. The problem appears when we try to calculate how much energy the vacuum should have, based on our theories. The methods of quantum field theory allow us to sum up the energies of all the possible fluctuations. When physicists first did this, the answer they found was not just large. It was far beyond any reasonable scale. The theoretical calculation for the energy density of the vacuum is about 10 to the power of 121 times larger than the value we actually observe from cosmic acceleration. This is a number so large it is difficult to describe. If the vacuum energy were truly that strong, its repulsive force would have been so great that the universe would have been torn apart moments after it began. Atoms would never have formed. Stars would never have ignited. We would not exist. This enormous gap between the theoretical prediction and the measured value is known as the cosmological constant problem, or sometimes the vacuum catastrophe. It has been called the most significant disagreement between theory and observation in the history of science. It tells us that something fundamental is missing from our understanding. Our two best theories of the universe, quantum field theory and general relativity, work beautifully in their own domains. But when they are brought together to describe the vacuum, they conflict profoundly. No one knows why the prediction is so wrong. There are many ideas. Some theories, like supersymmetry, suggest that for every particle contributing positive energy, a yet undiscovered partner particle exists that contributes negative energy, and they almost perfectly cancel out. So far, we have not found these partner particles. Other ideas propose that the vacuum energy is not constant, or that we live in a particular region of the universe where, by chance, the value is very small. These are difficult ideas to test. The vacuum catastrophe is not a failure. It is a signpost pointing toward a vast, unexplored part of physics. It tells us, with quiet humility, that our understanding of reality is still incomplete. We have traveled from the classical idea of a simple void to a quantum storm, and arrived at one of the deepest puzzles in science. The energy of nothing seems to power everything, yet we do not understand why its effect is so gentle. What do you think is missing from the picture? Is it a flaw in our understanding of quantum mechanics or of gravity? Feel free to share your thoughts in the comments below. And if your mind is still moving with these ideas, consider liking the video to help this exploration reach other curious minds. We began with a simple idea, that empty space is empty. We end with a reality that is far more subtle, powerful, and mysterious. The classical vacuum was a neat idea that has been replaced by the quantum vacuum, a fundamental aspect of our universe. It is the lowest energy state, but it is not zero. It is a quiet sea of zero-point energy, giving rise to a constant murmur of virtual particles. This is not just a theory. We can measure its effects. We see the Casimir force, a tangible push from the void, showing that nothing can do something. We may even see its traces in the properties of real particles, which seem to carry a memory of their fleeting existence in the quantum foam. On the largest scales, this energy of nothingness appears to become the most dominant force in the cosmos. It is the dark energy that pushes galaxies apart, shaping the final fate of our universe. The backdrop has become the engine. Yet, this same discovery has left us with the vacuum catastrophe, the profound puzzle of why this energy is so much smaller than our theories predict. It is a humbling reminder that what we know is surrounded by a vast territory of what we do not. So the next time you look into the dark space between the stars, remember what is likely there. Not an absence, but a presence. Not stillness, but a quiet, energetic foundation. It is the source of everything we can see, and the source of our deepest questions. The idea of nothing may have been a simple story we told ourselves. The truth, that the vacuum is a complex and powerful something, is far more interesting. And the journey to understand it has only just begun. Science just proved empty space is an illusion. We are taught, from a young age, that empty space is simply that, empty. The absence of everything. A perfect, silent void. It feels like the baseline of reality, the quiet stage upon which the universe unfolds. We learn that an atom is mostly empty space, a tiny nucleus with electrons orbiting at a vast distance. We imagine the colossal gulfs between stars and galaxies, and we call it space, the ultimate nothing. But what if that quiet emptiness isn't empty at all? What if the most silent place you can imagine is actually a restless sea of particles, appearing and disappearing in moments too brief to see? An invisible energy that shapes our entire reality. Modern physics is suggesting that the very concept of nothing is a figment of our everyday intuition. It suggests that at every point in space, subatomic particles are coming into existence for a fleeting moment and then vanishing. Science is beginning to show us that the void is not a void at all. And that beneath this illusion of stillness lies the most fundamental and strangest layer of reality we have ever encountered. The Great Reversal. For most of human history, the idea of nothing was simple. If you take a box, remove every atom, shield it from all light, and cool it to absolute zero, you are left with a perfect vacuum. You are left with nothing. In the world of classical physics, space was a passive backdrop. It was an empty container that did not push, pull, or do anything. It simply was. This was the common sense view for centuries. But in the early 20th century, two revolutions in physics, relativity and quantum mechanics, began to dismantle this simple picture. It started with a mathematical puzzle. In the 1930s, the physicist Paul Dirac was working to combine Einstein's special relativity with the new rules of quantum mechanics. His equations were elegant, but they produced a strange result: solutions that suggested the existence of negative energy states. According to all the physics that came before, this was impossible. A lesser physicist might have dismissed it as a mathematical quirk. But Dirac took the math seriously. He proposed that the vacuum was not empty. Instead, he suggested it was an infinite sea of particles occupying these negative energy states. This, Dirac's sea, was completely full, and therefore, undetectable to us. This was a turning point. For the first time, a mainstream physicist was claiming that the vacuum was not an absence of things, but a physical system in its own right. Dirac theorized that if you struck this sea with enough energy, you could knock one of these negative energy particles out. This would leave behind a hole, which would behave just like a particle but with the opposite charge. He was predicting the existence of antimatter. An electron knocked from the sea would appear, and the hole it left behind would be its antimatter twin, the positron. Just a few years later, in 1932, the positron was discovered, exactly as Dirac had predicted. His seemingly strange idea was correct. Suddenly, the vacuum was no longer a placid nothingness. It was a hidden, physical reality. The illusion of empty space was beginning to crack, and what lay beneath was far stranger than anyone had imagined. The architects of reality, quantum fields. To understand why empty space is an illusion, we have to go deeper. We have to set aside our old picture of particles as tiny balls, and embrace one of the most profound ideas in all of science, the quantum field. The revolution that began with Dirac led to what we now call quantum field theory. It tells us that the most fundamental components of the universe are not particles. They are fields. Think of it like this. Imagine the surface of a perfectly calm ocean, stretching to infinity. That calm surface represents a field in its lowest energy state. Now, imagine you tap the surface. A wave spreads out. That wave, that localized ripple of energy, is what we perceive as a particle. In the universe, there isn't just one ocean. There is an electron field, permeating every point in space. There is a photon field. There are fields for every fundamental particle we know. Everything you see, everything you are, is made of these fields. An electron is not a tiny dot moving through the electron field. It is a localized vibration of the electron field. A photon of light is a ripple in the electromagnetic field. When these fields are excited, they manifest as the particles we know. This completely changes the question of, what is empty space? In the language of quantum field theory, a vacuum is simply the state where all of these fields are as calm as they can possibly be. It is the ground state, the lowest possible energy for all the fields that make up the universe. When you remove all the particles from a region of space, what you are really doing is calming down all the fields. You are smoothing out the ripples, leaving behind only the quiet, fundamental oceans of reality. But here is the critical, mind-bending twist of quantum mechanics. The lowest possible energy state is not a state of zero energy. Even in their ground state, these fields are not perfectly still. They can't be. To be perfectly still would mean they have a definite energy, zero, and a definite state, unchanging. And the universe, at its most fundamental level, simply doesn't allow for that kind of certainty. This brings us to the ghost in the machine. The ghost in the machine, virtual particles. The reason the quantum vacuum can never be truly still comes down to one of the bedrock principles of reality, the Heisenberg uncertainty principle. Many have heard of this principle in terms of position and momentum. The more precisely you know where a particle is, the less precisely you can know where it is going. But there is another version of this principle that relates energy and time. It states that you cannot know both the exact energy of a system and the exact amount of time it has that energy with perfect precision. There's a trade-off. Over a long period, energy must be conserved. But for incredibly brief moments, fleeting instants far too short for us to measure directly, the universe allows for a little flexibility. Energy can be borrowed from the vacuum, as long as it's paid back almost instantly. The shorter the time, the more energy can be borrowed. This is what the mathematics of quantum mechanics demands. This borrowed energy can momentarily burst into existence as a pair of particles, a matter particle and its antimatter equivalent. An electron and a positron, for example. These are not the real particles that make up you and me. They exist for only a fraction of a second before they find each other and annihilate, paying back the energy loan and disappearing back into the quietness from which they came. Physicists call these fleeting apparitions virtual particles. They are the quantum fluctuations of the ground state fields. The vacuum, even at its lowest energy state, is therefore a restless, bubbling sea of these virtual particles constantly appearing and disappearing. It's a phenomenon often called quantum foam. This isn't a wild guess. It is a direct mathematical consequence of combining quantum mechanics and special relativity. For a long time, these virtual particles were seen as a kind of mathematical tool, a convenience used in calculations. But then we started to find proof. We discovered that these ghostly particles, these fleeting figments of the void, have real, measurable effects on the world around us. They are not just ghosts. They are the invisible machinery that runs the universe. The proof: catching the ghosts. The idea of a vacuum teeming with invisible particles sounds like something imagined rather than evolved. For a time, many physicists treated it that way. And yet, the evidence for its reality came not from a single moment, but from a series of stunning experiments that revealed the fingerprints of the void on the matter we can see. The first major piece of evidence was subtle, but undeniable. It's called the *Lamb shift. In 1947, a physicist named Willis Lamb was making incredibly precise measurements of the hydrogen atom. According to the theories of the day, two specific energy levels in hydrogen should have been identical. But Lamb's experiment showed they were not. There was a tiny, but persistent, difference. The discrepancy was a puzzle. Where was this extra energy coming from? The answer came from the quantum vacuum. Physicists realized that the single electron orbiting the hydrogen nucleus was not truly alone. It was constantly being jostled by the sea of virtual particles appearing around it. This constant, subtle interaction was enough to nudge the electron's energy ever so slightly, accounting perfectly for the difference Lamb had measured. The Lamb shift was the first experimental confirmation that the quantum foam was a real, physical phenomenon. But the most famous demonstration of the vacuum's power is the Casimir effect. Predicted by Dutch physicist Hendrik Casimir in 1948, the idea is as simple as it is brilliant. Imagine you take two perfectly flat, uncharged metal plates and place them incredibly close to each other in a vacuum. According to classical physics, nothing should happen. But Casimir realized the quantum vacuum would behave differently between the plates than outside them. Outside the plates, virtual particles of all wavelengths can appear. But the tiny gap between the plates acts as a cavity. Only virtual particles with wavelengths that fit neatly into that gap can exist there. This means there are more virtual particles appearing in the space outside the plates than between them. This imbalance creates a pressure. The storm of virtual particles on the outside is stronger than the storm on the inside. The result is a real, measurable force pushing the two plates together. For decades, this effect was too small to measure, but with modern nanotechnology, experiments have confirmed the Casimir force with astonishing precision. It is a force born from nothing, a quiet whisper from the void that engineers of microscopic devices must now account for. Perhaps the most dramatic prediction related to the vacuum is Hawking radiation. It is important to remember that this remains a theoretical idea, as it has not yet been observed. Stephen Hawking proposed that near a black hole's event horizon, a virtual particle pair could appear. If one particle falls into the black hole while the other escapes, the escaping particle can no longer annihilate. It becomes a real particle, flying off into space. From an outside perspective, it would look as though the black hole is slowly radiating particles, and therefore, evaporating over immense timescales. The source of this radiation, if it exists, is once again the quantum vacuum. The evidence continues to build. Experiments at particle colliders have managed to give virtual particles the energetic boost they need to become real, detectable particles. What's more, they found these new particles retain a memory of their time in the vacuum, a signature of their origin as entangled virtual pairs. This is not quite a direct window into the vacuum, but it is one of the closest we have come to tracing the lineage of real matter back to the quantum foam. The cosmic implications. The reality of the quantum vacuum is not just a microscopic curiosity. The effects of this quiet energy are written across the largest possible canvas, the universe itself. The illusion of empty space is a key to understanding why we are here, and where the universe is going. The leading theory for the birth of our universe involves a period of hyper-rapid expansion called cosmic inflation. For galaxies and stars to form, there needed to be some initial seeds of structure. A perfectly smooth universe would have stayed that way forever. So where did these seeds come from? They came from the quantum vacuum. In that primordial moment, the tiny, random quantum fluctuations were stretched to astronomical scales by the explosive inflation. Tiny regions that, by chance, had a slightly higher energy density became the seeds of galaxy clusters. Regions with slightly lower density became the great cosmic voids. Every galaxy, every star, and ultimately, every one of us, can trace our origins back to a random quantum flicker in the nothingness of the primordial vacuum. We are, in a literal sense, the children of quantum foam. And the vacuum's role is far from over. In 1998, astronomers made a shocking discovery. They found that the expansion of the universe is not slowing down, it's accelerating. Something is acting like a form of anti-gravity, pushing space-time apart. Physicists have given this a name, dark energy. And the leading candidate for what dark energy is the energy of the vacuum itself. The idea is that the quantum vacuum has a baseline, intrinsic energy. This vacuum energy, woven into the fabric of spacetime, exerts a negative pressure, pushing everything apart. So, the same restless sea of virtual particles that seeded the galaxies may now be driving the universe toward its ultimate fate. The nothing of empty space is not just the stage for the universe. It appears to be the engine driving its evolution. The unsolved mystery, the vacuum catastrophe. By now, it might seem that physicists have this figured out. And yet, beneath this success lies one of the greatest mysteries in all of physics. A problem so profound it has been called the vacuum catastrophe. It's a quiet, humbling story about where our best ideas meet their limits. The problem arises when we try to put numbers on things. Quantum field theory allows us to calculate what the energy of the vacuum should be. When physicists do this, they get a number that is staggeringly large. On the other hand, Einstein's theory of general relativity allows us to measure the vacuum energy's actual effect. We can observe the rate at which the universe's expansion is accelerating and work backward to figure out how much dark energy must be driving it. When astronomers do this, they find a value for the vacuum energy that is incredibly, exquisitely tiny. Herein lies the catastrophe. The theoretical prediction and the observational measurement don't just disagree. They disagree by a factor of 1 followed by up to 120 zeros. This is, without exaggeration, the single worst theoretical prediction in the history of science. It tells us that our two most successful theories of reality, quantum mechanics and general relativity, are fundamentally incompatible. They break down completely when they try to describe the same thing, the empty space between things. It is as if our best map of the mountains and our best map of the oceans are both perfect, but when we put them together, they show the sea level is higher than the tallest peak. Something is profoundly wrong with our understanding. There must be some unknown physical principle that is canceling out almost all of this predicted energy, leaving behind just the tiny residue we observe. Solving this is arguably the most important open problem in fundamental physics. The illusion of empty space is hiding a conflict at the very heart of science. The modern frontier, harnessing the void. The quantum vacuum is not just a source of cosmic mysteries, it is becoming a frontier for new ideas. What was once the domain of theorists is now entering the thoughts of engineers, with possibilities that feel as though they belong to a distant future. One of the most speculative ideas is extracting usable energy from the vacuum. While a perpetual motion machine running on zero-point energy is science fiction, some physicists are exploring legitimate ways to interact with the vacuum's properties. Building on theoretical work, some suggest it may be possible to coax the vacuum into giving up energy by using quantum entanglement to teleport it, borrowing it from one part of the vacuum to be released in another. This remains deeply theoretical, a stunning proof of concept in mathematics more than a practical reality. More grounded applications are emerging in nanotechnology. The Casimir effect is so real at the nanoscale that it is being studied as a way to move tiny mechanical systems without touching them. Scientists have even demonstrated the ability to tune the force, switching it from attractive to repulsive, which could allow for frictionless components in micro-machines. The weirdness of the vacuum is also being explored for its potential in propulsion. The Advanced Research Agency DARPA has funded research into the energy within Casimir cavities. Some have noted that the distribution of energy created in these cavities bears a resemblance to the theoretical requirements for concepts like a warp drive. This is still firmly in the realm of speculative science, but the fact that the properties of the vacuum are being seriously investigated shows how far our thinking has come. From quantum computing to chemistry, scientists are no longer just observing the quantum foam. They are starting to learn how to engineer it. The nothing of empty space is slowly becoming a resource. Our journey began with a simple idea. that empty space is the absence of everything. We've seen that idea quietly dismantled. We've replaced it with a vision of reality far more restless and powerful than we imagined. The universe is not built on a foundation of stillness, but on a roiling sea of potential. The most fundamental layer of reality is not solid, but a collection of invisible, energetic fields. And the vacuum, the nothing we thought was a passive stage, is in fact their ground state, a state of lowest energy, but not zero energy. It is a quantum foam, a relentless storm of virtual particles whose fleeting existence drives the very laws of nature. These ghosts in the machine are not mere curiosities. Their collective energy nudges the orbits of electrons. Their pressure pushes physical objects together. Their fluctuations in the primordial universe were the seeds of all the galaxies we see. And today, the energy of this empty space appears to be accelerating the expansion of our entire cosmos. The true illusion was ever thinking that nothing could be simple. The vacuum is where our most successful theories break down, and it is where the next great revolution in physics likely waits. It is the architect of the cosmos, the engine of its expansion, and the source code of reality. The next time you look up at the vast, dark emptiness between the stars, remember what you are really seeing: the most complex, energetic, and mysterious something in the entire universe. Scientists discovered a force in empty space. For most of human history, we have looked out into the vast expanse between stars and galaxies and called it nothing. We saw it as a silent, featureless stage upon which the great drama of the universe could unfold. It was the definition of absence, the ultimate void. But in science, our understanding of the world is always evolving. And it now appears this conception of nothingness was incomplete. What we call empty space is, in fact, filled with a hidden, simmering energy. Physicists have found a force lurking within that very nothingness, a force that can physically push and pull on real objects. This is not a myth, nor a theoretical fantasy. It is one of the strangest and most profound discoveries of modern physics, one that changes our understanding of reality itself. This is a journey into the heart of the quantum world, to uncover a force born from emptiness, and to see how scientists proved that even nothing is something. The classical void, a perfect, featureless nothing. To understand the change in our thinking, we first have to travel back in time. For millennia, the concept of nothing was a philosophical idea more than a scientific one. The ancient Greeks debated it, with Aristotle famously declaring that nature abhors a vacuum, the idea that true emptiness was impossible. For centuries, this notion held. But the scientific revolution began to chip away at this ancient conviction. In the 17th century, Evangelista Torricelli, a student of Galileo, created a sustained vacuum in a glass tube of mercury, proving that a void could, in fact, exist. The space at the top of his barometer appeared to be empty. This set the stage for classical physics and Isaac Newton. For Newton, space was absolute, a vast, unchanging, three-dimensional grid. It was the backdrop. Planets, stars, and people could move about on this stage, but the stage itself did nothing. It was passive and inert. In this view, if you were to take a box and remove every last atom and shield it from all radiation, you would be left with a perfect nothing. The energy inside would be zero. There would be no activity, no forces. It was the physical embodiment of absolute stillness. This view became the bedrock of physics. It is intuitive and logical. Even as James Clerk Maxwell introduced the idea of invisible fields permeating space, the vacuum itself was still seen as the state where these fields were dormant, their values set to zero. For all intents and purposes, empty space was empty. It contained no energy and could exert no force. This was the undisputed truth, but it was an image of the void that was about to be quietly and completely torn apart. The quantum revolution, cracks in the emptiness. The dawn of the 20th century brought discoveries that poked holes in the orderly world of classical physics. It began with Max Planck, who, in 1900, proposed that energy was not a smooth fluid, but came in discrete packets, or quanta. He saw it as a mathematical trick to solve a problem with the light emitted by hot objects, but the trick worked. Physics had taken its first step into the quantum realm. The idea that would truly shatter the classical vacuum came from another pillar of quantum mechanics, the Heisenberg uncertainty principle. In 1927, Werner Heisenberg unveiled a concept that remains profoundly strange. It states that you cannot simultaneously know certain pairs of properties of a particle, such as its precise position and its precise momentum. It is not a limitation of our instruments, but a fundamental fuzziness baked into reality. This principle also applies to energy and time. You cannot know the exact energy of a system within an infinitesimally short moment. This has a staggering implication. A truly empty space, as the classical view supposed, would have an energy of exactly zero at every single instant. You would know its energy with perfect certainty. But Heisenberg's principle forbids this. To comply with quantum mechanics, the energy of empty space cannot be a perfect zero. It must fluctuate. It must churn with a constant, unavoidable energy, even at absolute zero where all classical motion should cease. This lowest possible energy a system can have is not zero. It is called the asterisk zero-point energy. This was the end of the classical vacuum. An inert, energy-less void was not just wrong, it was impossible. But what is this energy? If there are no particles, what is it that's fluctuating? Quantum field theory offers a new vision. Here, the most fundamental things are not particles, but asterisk fields. The entire universe is permeated by an electron field, an electromagnetic field, and others. A particle, like an electron, is simply a localized vibration, a ripple in its corresponding field. Imagine a perfectly calm ocean stretching to infinity. This represents the vacuum. Now, imagine a ripple spreads outwards. That ripple is a particle. When it dies down, the particle is gone, but the field, the ocean, remains. The zero-point energy is the energy of these fields, constantly twitching in accordance with the uncertainty principle. Even in a vacuum with no real particles, the fields themselves are fluctuating. From these fluctuations, pairs of asterisk virtual particles asterisk can briefly burst into existence, borrowing energy from the vacuum before annihilating and paying the energy back. They are the phantom whitecaps on this quantum sea. The nothing of classical physics had been replaced by a something of unimaginable complexity. But for a long time, this was just a theory. It would take an ingeniously simple thought experiment to bridge the gap from abstract idea to measurable reality. A sea of phantom energy, virtual particles and zero-point energy. The idea of a vacuum teeming with virtual particles can seem like a convenient fiction. In quantum field theory, however, these particles are how forces are described. When two electrons repel each other, they are exchanging virtual photons. These messenger particles exist only for the brief moment of the interaction, living on borrowed energy. The quantum vacuum, then, is the sum total of all these potential fluctuations. Pairs of virtual particles and their antiparticles, an electron and a positron, for instance, are constantly being created from their underlying fields. They exist for a fraction of a second before vanishing back into the nothingness from which they came. The analogy of a boiling sea is fitting. The surface appears flat from a distance, just as the vacuum appears empty. But up close, it's a chaos of tiny bubbles forming and popping. These bubbles are the virtual particle pairs, a direct consequence of the energy inherent in the water itself. For decades, this remained a deeply theoretical idea. While it helped physicists make calculations, many were skeptical. Was the vacuum really a sea of phantom particles? The story, as it's often told, takes us to the Netherlands in the late 1940s. A physicist named Hendrik Casimir was working at Phillips Research Labs on the weak attractive forces between neutral molecules. Frustrated that his calculations didn't match experiments, he discussed it with Niels Bohr, one of the founders of quantum theory. Bohr reportedly muttered that it must have something to do with the zero-point energy, suggesting that nothing surrounding the molecules was playing an active role. This sent Casimir down a new path. He set aside the messy details of his work and imagined something pure and elegant: two perfectly flat, reflective, uncharged metal plates, placed parallel to each other in a perfect vacuum. Classically, nothing should happen. But Casimir asked a revolutionary question. What does the quantum vacuum do in the presence of these plates? The proof: Hendrik Casimir's stroke of genius. Hendrik Casimir's 1948 thought experiment connected the abstract world of quantum theory to a tangible prediction. He realized that two parallel plates would act as boundaries for the virtual particles fluctuating in the vacuum. Virtual particles are essentially waves, and waves have wavelengths. In the open vacuum outside the plates, virtual particles of all possible wavelengths can exist. But in the tiny gap between the plates, a wave with a wavelength longer than the gap itself simply cannot form. It is physically excluded. This creates a crucial difference. The variety of virtual particles that can exist in the gap is restricted. The unrestricted spectrum of fluctuations can still exist in the space outside. This means there are more modes of fluctuation, more virtual particles, on the outside surfaces of the plates than on their inner surfaces. Each of these virtual particles exerts a tiny amount of pressure. Since there is a greater total pressure from the outside in than from the inside out, the result is a net force, pushing the two plates together. This became known as the Casimir effect. The force does not come from magnetism, electricity, or gravity. It is a force from the structure of nothingness itself. To use an analogy, imagine two large ships floating parallel and very close together on the open ocean. Long, rolling swells can't fit in the narrow channel between them. Because these powerful waves are only hitting the ships from the outside, they are pushed together. The ships are the metal plates, and the ocean waves are the virtual particles. For nearly 50 years, the Casimir effect remained a beautiful prediction. The force was predicted to be incredibly weak and measurable only at microscopic distances. The definitive proof had to wait until 1997, when Steve Lamoureux at Los Alamos National Laboratory devised an experiment of exquisite sensitivity using a torsion pendulum. By carefully bringing the surfaces close together, he measured the tiny force pushing them. The results were a triumph. The measured force matched Casimir's prediction to within 5%. Since then, other experiments have confirmed the effect with even greater precision. It seemed to be undeniable proof that the force from nothing was real. However, further research has revealed complexities, and while the effect is real, its interpretation as definitive proof of zero-point energy is a leading theory, but one that is still quietly debated among some physicists. Alternative explanations exist that do not require invoking the quantum vacuum. The implications: a force that shapes the universe. The confirmation of the Casimir effect revealed that the vacuum plays an active role in the universe, with implications from tiny technologies to the cosmos itself. In nanotechnology, where components are separated by nanometers, the Casimir force is a dominant effect. It can cause microscopic parts to stick together, a problem called stiction. What was once a nuisance, however, is now seen as a potential tool, with researchers hoping to manipulate the force to create microscopic machines powered by the vacuum itself. Perhaps the most startling implications appear at the scale of the universe. Cosmologists have discovered that the expansion of the universe is accelerating, driven by a mysterious entity called dark energy. The leading candidate for what dark energy is the energy of the vacuum itself. Here, however, we encounter one of the greatest mysteries in science. When physicists try to calculate the total energy of the vacuum based on theory, the number they get is astronomically large. By some estimates, 120 orders of magnitude larger than the amount of dark energy we observe. This discrepancy, the cosmological constant problem, is one of the most profound unsolved puzzles in physics. It tells us that while vacuum energy is real, we are missing something fundamental about its connection to gravity. The mystery is so deep that some scientists are exploring other possibilities. They question whether dark energy and its cousin, dark matter, are even real. They propose that these phenomena might be illusions, artifacts of an incomplete understanding of gravity. The debate is ongoing and represents a significant shift in cosmological thinking. We began with a simple idea that empty space is nothing. Through the lens of quantum mechanics, we have watched that idea change. We discovered the Heisenberg uncertainty principle, which demands that even the lowest energy state must buzz with a zero-point energy. We saw how this energy can be pictured as a sea of virtual particles, and how Hendrik Casimir predicted this sea could create a real, measurable force. The force from empty space is no longer a theoretical curiosity. It is a fundamental aspect of our world. It is a force engineers must account for when building microscopic machines, and it may be the very energy that is pushing our universe apart. Or it may be a clue that points toward a deeper, stranger theory of gravity we have yet to discover. The discovery that empty space has energy and can exert force represents one of the most significant shifts in our understanding of the physical world. It proves that the stage of reality is an actor in its own right, a dynamic and powerful entity. The emptiest place you can imagine is, in fact, one of the busiest, and nothing is one of the most fascinating somethings in the entire universe. The ghost force that bends reality. What if the most creative force in the universe was not a thing, but the space between things? Imagine a laboratory. Inside, scientists construct a near-perfect vacuum, a chamber of engineered emptiness. Within this space, they place two flawless, uncharged mirrors facing one another, separated by a gap smaller than the width of a human hair. They remove the air, the particles, the radiation. Then, they observe. And after a time, something happens. The mirrors begin to move. Without being touched, with no apparent force acting on them, they are slowly pushed together. This is not a thought experiment. It is a real and verifiable observation, one that challenges our intuitive understanding of the world. It suggests that what we call empty space is not empty at all. That the nothingness we imagine as a silent, passive void is instead a place of constant, subtle activity, an underlying energy that physically shapes our reality. This is the story of that force. It is a journey into how nothing becomes something, how emptiness influences the structure of the universe, and how a single, precise experiment with two mirrors reveals a truth that forces us to reconsider the nature of existence itself. The classical view of emptiness. To understand how revolutionary this idea is, we have to step back in time, to the universe as it was imagined for centuries through the lens of classical physics. In this world, the world of Isaac Newton, of tangible objects and predictable forces, the concept of nothing was simple and absolute. Emptiness was just empty. Imagine a box. To create a perfect vacuum inside it, the classical method is straightforward. First, you remove the air. Then, you remove every stray atom and molecule. You shield it from all external light and heat, cooling it toward the theoretical limit of absolute zero, where all motion is supposed to cease. In the classical view, what remains is true nothingness. A perfect void. No particles, no energy, no activity. It is a state of pure non-existence, a silent, static backdrop against which the mechanics of matter unfold. This idea of a passive void was the bedrock of our understanding of space. Space was the stage, particles were the actors. The stage itself did nothing. It was an inert grid of coordinates where events could happen. This was a universe of cause and effect. If you knew the position and momentum of every particle, you could, in principle, predict the entire future of the cosmos. In this mechanical universe, a force required a source. For something to move, something else had to act upon it. The idea of two mirrors in a vacuum moving on their own would have been treated as a logical impossibility. It would be like a sailboat moving without wind or a current. For centuries, philosophers had debated whether a true void could even exist. But by the 19th century, physics seemed to have settled the question. The void was possible, it was just the absolute absence of things. The ultimate state of zero. Zero particles, zero energy, zero everything. It was a clean and tidy picture of reality. But as the 20th century began, this orderly vision was about to be revised. A new understanding of physics was emerging, one that would look at this perfect, classical vacuum and see not an empty stage, but a place of infinite potential. It would discover that you can never truly empty the box. The universe, it turns out, has a fundamental property that prevents absolute nothingness. A fundamental uncertainty. The deterministic world of classical physics was re-examined with the arrival of quantum mechanics. At the heart of this new, probabilistic view of the universe is a principle so fundamental that it reshapes the definition of reality itself. It is called the Heisenberg uncertainty principle, and it is the reason perfect emptiness is impossible. The uncertainty principle, formulated by Werner Heisenberg in the 1920s, is not about the limits of our measurement tools. It is a built-in property of the universe. In its most familiar form, it states that you cannot simultaneously know both the precise position and the precise momentum of a particle. The more accurately you measure one, the less certain the other becomes. Reality at its most fundamental level has a persistent, irreducible fuzziness. There is another version of this principle, one that relates energy and time. It states that you cannot know the exact energy of a system over an infinitesimally short period. There is always an uncertainty. This means that for very brief moments, the energy of any point in space can fluctuate, borrowing energy from the vacuum as long as it is paid back almost instantly. Now, let's apply this to our empty box. The classical view assumed a state of perfect zero energy was achievable. But the uncertainty principle suggests this is not possible. If the energy of our vacuum was precisely zero and stayed precisely zero, we would know its energy and its rate of change with perfect certainty. This would represent a violation of this fundamental uncertainty. Instead, to obey the laws of quantum mechanics, even a perfect vacuum must contain a minimum possible energy, a state physicists call the ground state, or the zero-point energy. Think of a guitar string. You can stop it from playing a loud note, but you can never make it perfectly still. At the quantum level, it will always hum with tiny, imperceptible vibrations. The vacuum of space is the same. It is never truly quiet. It is constantly humming with a minimum, non-zero amount of energy. This zero-point energy is real. It is the baseline energy of the universe. We cannot directly see it in the same way we see light, because it is everywhere, all the time. It is the energetic floor of reality. A fish does not observe the water it swims in, it is simply the medium in which everything exists. But if this energy is a constant, uniform background hum, how could it possibly exert a force? How could it move two mirrors? The answer is that while the energy itself may be uniform in open space, its effects are not. This energy is the product of a constant, subtle activity that fills every cubic centimeter of the cosmos. This is the realm of virtual particles, fields and fluctuations. The idea of zero-point energy leads to a concept from our most advanced description of reality, quantum field theory. According to this theory, the universe is not made of tiny, solid particles. Instead, the fundamental building blocks of reality are fields. Think of a magnetic field. You cannot see it, but you know it is there because it affects a compass needle. It is a property of space itself. Quantum field theory proposes that everything is a field. There's an electron field, a photon field, a quark field, one for every fundamental particle. These fields permeate all of spacetime. What we perceive as a particle, like an electron, is just a ripple, a localized excitation in its corresponding field, like a wave cresting on the surface of an ocean. What, then, is a vacuum? A vacuum is what remains when you remove all the real particles. It's the state where all the fields are in their lowest possible energy state, their ground state. But as we learned from the uncertainty principle, that ground state is not zero. The fields are still there, and they are still subject to quantum uncertainty. They cannot be perfectly still, they must constantly fluctuate. Because of these unavoidable energy fluctuations, particle-antiparticle pairs can spontaneously appear, borrowing their energy from the vacuum. An electron and its antimatter twin, a positron, might flicker into being for an impossibly short time before they find each other and annihilate, disappearing back into the vacuum and repaying their energy debt. These are not the real particles that make up matter. They are called virtual particles. They are transient, fleeting presences that populate the vacuum, their existence too short to be directly measured. For a long time, they were considered by some to be a mathematical convenience. But they are more than that. The vacuum of space is not a tranquil void. It is a place of ceaseless, subtle activity. Imagine an ocean that looks perfectly calm from a distance. But up close, you see it is a frenzy of motion, tiny currents swirling, fleeting bubbles forming and popping. That is the quantum vacuum. Even in the darkest, most empty corner of the cosmos, this quantum foam is fizzing with existence. This idea remained a powerful theoretical construct for years. It explained certain subtle effects in atomic physics, but no one had directly witnessed the power of this virtual sea. That changed in 1948, when the Dutch physicist Hendrik Casimir was working on a seemingly unrelated problem. He was not trying to redefine reality. He was trying to understand why certain industrial materials behaved strangely. His investigation would lead him to a stunning prediction, a way to prove that this ocean of virtual particles was real. Two mirrors and the pressure of the void. The story of how we demonstrated the vacuum is not empty begins not in an academic setting, but with an industrial problem at Philips. The physicist Hendrik Casimir was trying to understand the van der Waals forces, the weak attractions between neutral molecules. While discussing his work with the great physicist Niels Bohr, Bohr made an offhand comment that this should have something to do with zero-point energy. That comment led Casimir to consider an idealized scenario. Instead of complex molecules, what if you simply had two perfectly conductive, uncharged metal plates in a perfect vacuum? Classically, nothing should happen. They have no charge, and the gravitational force between them is negligible. The plates should remain motionless. But Casimir realized that if the quantum vacuum was a real sea of virtual particles, the situation would be different. He pictured the vacuum filled with virtual photons of all possible wavelengths, flickering in and out of existence. In the open space outside the two plates, virtual photons of every conceivable wavelength can appear freely. These particles exert a kind of pressure as they pop in and out of being. Now, consider the tiny gap between the two plates. The plates act as boundaries. This tiny cavity can only host virtual photons whose wavelengths fit neatly into the gap. A virtual photon with a wavelength longer than the distance between the plates simply cannot form there. This creates an imbalance. The space outside the plates is filled with virtual photons of all possible wavelengths, all pushing on the outer surfaces of the plates. The space between the plates, however, allows for a more restricted collection of virtual photons. There are simply fewer virtual particles appearing inside the gap than outside it. The result is that the pressure from the vacuum outside is greater than the pressure from the calmer vacuum inside. The two mirrors are pushed together, not by a charge or gravity, but by the pressure of the void. This predicted force became known as the Casimir effect. For nearly 50 years, this remained a theoretical prediction. The force was predicted to be incredibly small, becoming significant only at microscopic separations. Measuring such a delicate force was an extraordinary experimental challenge. Then, in 1997, Steve Lamoureux at Los Alamos National Laboratory succeeded. Using a highly sensitive torsion pendulum, he measured the tiny attraction between a sphere and a plate in a vacuum. The measured force matched Casimir's prediction to within 5% accuracy. It was direct, experimental proof that the vacuum of space is a physical medium that can exert a tangible force. Subsequent experiments have since confirmed the effect with even greater precision, in some cases to within 1% of the theoretical value. The impossible had been observed: two mirrors, moved by the energy of nothing at all. We have just seen how an experiment revealed that nothing is a physical force. This is one of the fundamental shifts in our understanding of reality, and we are about to explore what it means for everything from the behavior of atoms to the origin of the universe. If this kind of calm exploration into the world of physics helps you unwind, consider liking the video and subscribing to the channel. We explore these topics every week, and you won't want to miss what comes next. The fingerprints of nothingness. The Casimir effect was the direct demonstration that the zero-point energy of the vacuum was a real, physical phenomenon. But once physicists understood what to look for, they began to find its influence in other areas. The force was not just pushing mirrors together in a lab. It was subtly influencing the entire quantum world, and its effects had already been measured decades earlier. One of the first important clues was a small anomaly in the behavior of the hydrogen atom, known as the Lamb shift. According to earlier quantum theory, certain energy levels within a hydrogen atom should have been perfectly identical. But in 1947, Willis Lamb and Robert Rutherford conducted a delicate experiment and found this was not true. There was a tiny, unexpected difference in the energy levels. They were shifted. The explanation, it turned out, was the vacuum itself. The electron, as it orbits the proton, is not traveling through a quiet void. It is moving through the chaotic sea of virtual particles. It constantly interacts with these fleeting virtual photons, and this relentless interaction slightly alters its energy. The Lamb shift was evidence of the energy the electron was interacting with in the void. The influence of the void extends beyond the atom, to the most extreme objects in the cosmos, black holes. This leads to one of the most remarkable predictions in physics: Hawking radiation. In 1974, Stephen Hawking was studying the intersection of quantum mechanics and general relativity near the event horizon of a black hole. He discovered something extraordinary. A popular way to visualize his finding involves virtual particles. Imagine a particle-antiparticle pair appearing at the edge of the event horizon. It's possible for one particle to fall into the black hole, while its partner escapes. From the perspective of a distant observer, it appears the black hole has emitted a particle. When the particle with negative energy in this pair falls in, it reduces the black hole's total mass. The other particle, with positive energy, flies away. To an outsider, it looks as if the black hole is slowly radiating. This is Hawking radiation. While the complete physical description involves the complex interaction of quantum fields with curved spacetime, this image captures the essential consequence. The interaction between the quantum vacuum and the extreme gravity of a black hole causes it to radiate. Over immense timescales, this process will cause the black hole to lose mass, shrink, and eventually evaporate. Black holes are not eternal. They leak, and they leak because the vacuum is not empty. The cosmic role of the void. The influence of the quantum vacuum is not limited to small-scale phenomena or exotic objects. According to our best cosmological models, the energy of the void may be the most important force in the universe, responsible for both its origin and its ultimate fate. Let us go back 13.8 billion years, to the first fraction of a second after the Big Bang. Our model for this era is called cosmic inflation. It proposes that in the first moments of time, the universe underwent a period of extraordinary, rapid expansion. What could have driven such an event? The leading candidate is the energy of the quantum vacuum. In the extreme conditions of the early universe, the vacuum may have existed in a high-energy, false vacuum, state. This high-energy vacuum would have had a powerful repulsive gravitational effect, pushing space apart with unimaginable force. This inflationary period also stretched the tiny, microscopic quantum fluctuations in the vacuum fields to astronomical sizes. These primordial fluctuations became the seeds of all cosmic structure. Over billions of years, gravity amplified these slight overdensities, pulling matter together to form the first stars, galaxies, and the vast cosmic web we see today. In a very real sense, a map of the large-scale structure of the universe is a physical record of quantum fluctuations from the first moment of time, written across the heavens. The story does not end there. In 1998, astronomers discovered that the expansion of the universe is not slowing down. It is accelerating. Something is pushing space apart. Physicists call this mysterious influence dark energy and the leading explanation for it is that it is the residual zero-point energy of the modern vacuum. The same kind of force that drove inflation may be responsible for the current accelerated expansion. This idea, however, leads to what has been called the worst theoretical prediction in the history of physics, also known as the vacuum catastrophe. When physicists try to calculate the total amount of zero-point energy in the vacuum, they arrive at a number that is stupendously large. When they compare this theoretical value to the amount of dark energy we observe, the numbers disagree by a factor of 10 to the power of 120. This is a discrepancy of a magnitude that is difficult to overstate. It tells us that despite everything we have learned, we are missing something fundamental about the nature of the vacuum, or gravity, or both. The force from the void is real, but its true nature remains one of the greatest mysteries in science. The reality of nothing. We began with a simple observation: two mirrors in a vacuum, moving without being touched. This single experiment propelled us on a journey. It has shown us that the vacuum is not empty, but is instead filled with a minimum energy dictated by the laws of quantum uncertainty. We have seen that this energy manifests as a sea of virtual particles, and that this activity can push mirrors together, alter the energy of an atom, and cause black holes to evaporate. We have also seen how this same energy may have ignited the Big Bang and now dictates the ultimate fate of our cosmos. The profound implication is that emptiness is not the absence of reality, but perhaps its foundation. The classical idea of things moving through empty space is an illusion. The deeper truth may be that the things are excitations of underlying fields, and the space itself is humming with potential. And yet, this realization leaves us with the deepest mystery of all. The vacuum catastrophe is a humbling reminder of how much we still do not understand. It signals that a new revision of our understanding is waiting, one that will finally unite our picture of the quantum world with the nature of spacetime itself. So the next time you look up at the night sky, at the vast, dark space between the stars, remember what you are really seeing. You are not looking at nothing. You are looking at the engine of creation, a restless ocean of possibilities. And it leaves us to wonder what other principles are waiting to be understood within the quiet heart of nothingness. The questions do not stop here. Every answer in science just unlocks a deeper, more fascinating question. If you want to be part of that journey of discovery, Make sure you're subscribed and have turned on notifications. The ghost force that proves empty space isn't empty. Imagine two metal plates. They are perfectly smooth, uncharged, and floating in a perfect vacuum. There is no air between them. No gravity acts upon them. There is nothing. Intuition tells us that they should simply remain still, motionless, forever. But under the right conditions, they begin to move. A quiet, unseen force pushes them together. The force seems to come from nowhere, from the empty space itself. This is not a thought experiment. It is a real and measurable phenomenon called the Casimir effect. It is the physical proof that our idea of an empty vacuum is incomplete. That nothing is one of the most active and fundamental parts of our universe. And this quiet force doesn't just move plates. It helps decide the fate of black holes, creates problems for our smallest technologies, and points toward the deepest mysteries of our cosmos. The quantum vacuum, a quiet hum. To understand where this force comes from, we have to look again at what it means for something to be empty. For a long time, the picture of a vacuum was simple. It was the absence of everything. If you could remove every last atom from a box, you would be left with pure, inert nothingness. This classical idea feels logical. It is what our senses suggest. And for the physics of our everyday world, it works well enough. But in the early 20th century, a new understanding of physics began to reveal a deeper layer to reality. That new understanding was quantum mechanics, and it showed that at its most fundamental level, the universe is a gentle, uncertain, and deeply strange place. One of the cornerstones of this physics is Werner Heisenberg's uncertainty principle. The principle is often explained in a specific way, concerning a particle's position and its momentum. You can know where a particle is, or you can know where it is going, but you can never know both with perfect accuracy at the same time. But the principle goes deeper than that. It also applies to the relationship between energy and time. And here, we find a fundamental rule of the universe. The uncertainty principle says that for very, very short moments, the law of conservation of energy, the rule that energy cannot be created or destroyed, can be briefly suspended. It is as if the universe allows energy to be borrowed from the vacuum, creating something from nothing, on one strict condition. The loan must be paid back almost instantly. The more energy that is borrowed, the faster it must be returned. So for incredibly small fractions of a second, the vacuum is permitted to bend the rules. In that borrowed time, it is filled with a quiet, constant activity. Particles and their antimatter counterparts, an electron and a positron, for example, can spontaneously come into existence, borrowing their energy from the void itself. These pairs of virtual particles exist for a fleeting moment before they must repay their energy loan. They find each other and annihilate, vanishing back into the nothingness from which they came. This is what our most successful theories of reality tell us is happening constantly, everywhere. The vacuum isn't an empty stage, it's filled with a silent hum of potential. It is filled with these phantom particles, blinking in and out of existence so quickly that we cannot see them directly. They are called virtual, because they do not last long enough to be measured as real. This idea redefines the void. Empty space is not empty. It is a dynamic, fluctuating place. The ground state of the universe is not zero energy. It is the minimum possible energy, and that minimum is not zero. This residual energy, this endless hum of virtual particles, is called the zero-point energy of the vacuum. For a long time, this was a strange prediction of the mathematics. These virtual particles were seen as useful tools for calculation, but without real, tangible effects on the larger world. They were ghosts in the theory. But what happens when you place something in the path of this ghostly dance? That was the question a Dutch physicist considered in the 1940s, and his answer would lead to the first direct proof that these phantom particles are undeniably real. The Casimir effect, a force from nothing. The year was 1948. The physicist Hendrik Casimir was working at Philips Research Labs in the Netherlands, studying the subtle attractive forces between molecules. During his work, he spoke with Niels Bohr, one of the founders of quantum theory, who made a simple suggestion. Perhaps the force had something to do with zero-point energy. That comment led Casimir to think not about tiny molecules, but about large objects. What would happen if you took two large, uncharged metal plates and placed them in a vacuum? He began to think about how the plates would interact with the quiet hum of the quantum vacuum he knew must be all around them. This was his quiet insight. Think of the quantum vacuum as a sea, with waves of every possible length moving through it. These waves represent the virtual particles. Out in the open sea of empty space, there are no restrictions. Waves of all sizes can exist. Now, place two large plates parallel to each other in this sea. In the narrow space between them, the situation changes. Small, short waves can still fit comfortably. But long waves simply cannot. A wave that is a mile long cannot form in a channel that is only a few feet wide. The space between the plates acts as a filter, excluding all waves longer than the distance of the gap. Casimir realized the same principle must apply to his two metal plates and the waves of the quantum vacuum. In the space outside the plates, virtual particles of all possible wavelengths can exist. But in the tiny gap between the plates, a restriction is created. The gap can only host virtual particles whose wavelengths fit inside. The consequence of this is profound. There are more possible ways for virtual particles to exist in the space outside the plates than in the space between them. This means the energy of the vacuum, the zero-point energy, is higher on the outside. This creates an imbalance. The vacuum outside pushes on the plates more than the vacuum inside pushes them apart. The result is a gentle but persistent force, pushing the plates together. This predicted force, born from the vacuum, became known as the Casimir effect. Casimir calculated that it would be incredibly weak, becoming noticeable only at microscopic distances. The force grows weaker very quickly with distance. Doubling the space between the plates reduces the force 16 times over. For nearly a decade, this remained a theoretical idea. The force was so tiny that measuring it seemed beyond reach. The first attempt, in 1958 by Marcus Sparnai, was extraordinarily difficult. His results had large margins of error, but they did not contradict the theory. It was a hint, but not a confirmation. For decades, the force remained a ghost. That changed in 1997. At Los Alamos National Laboratory, Stephen K. Lamoureux designed a new kind of experiment. Instead of using two flat plates, which are almost impossible to keep perfectly parallel, he measured the force between a flat plate and a large sphere. The distance between a plate and a sphere is always easy to define. Using a highly sensitive instrument, Lamoureux was able to measure a tiny attractive force. After accounting for all other possible sources, a small, persistent force remained. The strength of this force matched Hendrik Casimir's 49-year-old prediction to within 5%. A year later, in 1998, an even more precise experiment by Umar Mohideen and Anushree Roy used an atomic force microscope, confirming the theory to within 1%. The force was real. The quantum vacuum was real. Virtual particles are not just a mathematical convenience, they exert a physical pressure on the world. And this force is not always small. When the distance between two surfaces shrinks to just 10 nanometers, about 100 atoms wide, the Casimir pressure is equal to the pressure of Earth's atmosphere. At the nanoscale, it is not a subtle effect. It is a powerful and unavoidable force of nature. The implications, when nothing shapes reality. Confirming the Casimir effect did more than validate a curious prediction. It proved that the quantum vacuum could be influenced, and its effects could be seen. This quiet force was a fundamental part of the universe, with consequences that reach from our most advanced laboratories to the edges of the cosmos. One of those consequences is the asterisk dynamic Casimir effect. The original effect comes from stationary plates. But theorists in the 1970s wondered what would happen if a boundary, like a mirror, moved. They predicted that if you could accelerate a mirror through the vacuum at nearly the speed of light, the motion would disturb the dance of virtual particles so much that some of them would gain energy and become real particles. You could, in theory, create light from nothing, just by moving a mirror fast enough. For 40 years, this was only an idea. Moving a physical mirror that fast is not possible with our technology. But in 2011, a team in Sweden found an ingenious way around this. They created an effective mirror inside a superconducting circuit. By rapidly changing the circuit's properties, they mimicked a boundary moving at a significant fraction of the speed of light. And it worked. They detected microwave photons, real particles of light, appearing from the vacuum inside their device. They had managed to shake the vacuum and produce light from its emptiness. While some researchers dream of working with the vacuum, engineers in the world of nanotechnology and microelectromechanical systems, MEMS, often face it as a challenge. MEMS are microscopic machines with moving parts fabricated on silicon chips. As these devices become smaller, the gaps between their components shrink to the nanometer scale. At these distances, the Casimir force can become the dominant force in the system. It acts like an invisible pull. Two microscopic parts that are meant to move freely can suddenly get stuck together, a problem engineers call stiction. A force from empty space becomes a physical obstacle in our tiniest machines. This same force also points to one of the most profound and humbling questions in modern physics: the asterisk cosmological constant problem. Our observations tell us that the universe's expansion is accelerating. There appears to be some kind of energy in spacetime itself that pushes everything apart, which we call dark energy. This energy looks very similar to the zero-point energy of the quantum vacuum. The problem is, when we use quantum theory, the same theory that so perfectly predicts the Casimir effect, to calculate the total energy of the vacuum, the number we get is deeply wrong. The predicted energy is about 120 orders of magnitude, a 1 followed by 120 zeros, larger than the value we observe. This has been called one of the greatest disagreements between theory and observation in the history of science. It is like measuring the size of a room and calculating it to be larger than the known universe. The theory that works so beautifully on a small scale seems to fail when applied to the cosmos. It suggests a connection is there, but that we are missing a fundamental piece of the puzzle. The Casimir effect proves vacuum energy is real. The cosmological constant problem proves we do not yet understand it. Finally, the same logic leads us to one of Stephen Hawking's most famous ideas: Hawking radiation. Hawking asked a similar question to Casimir, but he placed his boundary at the most extreme place in the universe, the event horizon of a black hole. He realized that the constant phys of virtual particle pairs would be happening right at this boundary. Normally, the pair would quickly annihilate. But at the event horizon, it is possible for one particle to fall into the black hole, while its partner escapes. The abandoned particle that escapes can no longer annihilate. It becomes a real particle, appearing to an outside observer as if the black hole is emitting radiation. Energy was borrowed from the vacuum to create this pair. Since the loan cannot be repaid by annihilation, the debt must be paid by the black hole itself. The particle that fell in has a negative energy that reduces the black hole's total mass. The net result is that the black hole loses a tiny amount of mass. Over immense spans of time, this process causes the black hole to slowly evaporate. While this popular explanation is a simplification of the complex mathematics involved, it captures the essential idea. The presence of the event horizon transforms the virtual fluctuations of the vacuum into a real, thermal glow. The force that pushes two plates together is related to the mechanism that makes black holes slowly dissolve. Both are rooted in the same truth: the vacuum is not empty. It is remarkable to think that a simple question about two metal plates can lead to the edge of black holes and the beginning of the universe. If this kind of quiet exploration of the world helps you to see it in a different way, consider liking the video and subscribing to the channel. The best ideas for future explorations often come from you, so feel free to share any thoughts or questions in the comments below. Now, let's bring it all together. The universe in nothing. We began with a quiet paradox: two plates in a perfect vacuum, moving without being touched. What seemed like a physical impossibility has revealed a profound truth about the nature of our universe. We have learned that the vacuum of space, which our intuition tells us is the definition of nothing, is in fact a place of constant, quiet, and powerful activity. We followed the logic from Heisenberg's uncertainty principle, the fundamental rule that allows energy to be briefly borrowed from the void. This principle gives rise to a silent sea of virtual particles, flickering in and out of existence everywhere in spacetime. We saw how Hendrik Casimir realized that by placing two plates in this sea, he could disturb their gentle dance. By excluding some virtual particles from the gap between them, a pressure imbalance is created, a real, physical force from the vacuum itself. And we saw how, after decades, the patient experiments of physicists finally measured this quiet force, proving the energy of the void was a tangible reality. This was not an endpoint, it was a beginning. It confirmed a picture of the universe where nothing is a powerful something. This same vacuum energy, when disturbed by a fast-moving mirror, can create real light. At the nanoscale, its force is strong enough to become a critical challenge for engineering. When we try to calculate its total value, it presents us with a deep cosmic mystery, hinting at a connection to the accelerating expansion of our universe. And at the edge of a black hole, its fluctuations are what cause Hawking radiation, the faint glow that signals the slow end of even the most massive objects. The two metal plates are a fitting metaphor for science itself. We start with a simple observation, a small detail that doesn't quite fit our understanding. As we look closer, we find it connects to everything. The force that moves two tiny plates in a vacuum is woven into the story of nanotechnology, black holes, and the ultimate fate of the cosmos. The universe is far stranger, more interconnected, and more alive than it first appears. Even in its quietest, emptiest corners, there is a deep and powerful reality, a quiet force reminding us that there is, truly, no such thing as nothing. The quantum vacuum theory explained slowly. Long before we understood the atom, before we knew the shape of our own galaxy, humanity held a simple idea about emptiness. We thought of the void as just that, a void, an absence. But sometimes in science, the most profound discoveries come not from finding something new, but from re-examining something we thought we already understood. What if the emptiest place you could possibly imagine wasn't empty at all? What if the cold, dark vacuum of deep space was instead filled with an unseen, unending hum of activity? It seems like a contradiction. And yet, this is where physics has led us. It asks us to look at the idea of nothing, and see in it a source of energy so vast that some early calculations suggested a tiny volume of it could boil away all the world's oceans. While that particular number comes from a problem we will explore later, the core idea remains. Nothing is far stranger, and far more important than it appears. Welcome to the Sleepy Scientist. If this kind of calm exploration into the world of physics helps you unwind, consider liking the video and subscribing to the channel. In this video, we are going to slowly dismantle our intuitive idea of nothing. We will look at the concrete, measurable proof that this energy is real, and see how imperceptibly small jitters in the fabric of reality may be responsible for the largest structures in the entire universe. By the end, you may come to agree that the most important thing in the universe is nothing. The classical idea of nothing, an empty stage. Before we can appreciate the strangeness of the quantum vacuum, we first need to understand the idea it replaced. For most of human history, the concept of perfect emptiness was a philosophical battleground. The ancient Greeks debated it. Thinkers like Democritus imagined the world was made of tiny atoms moving through a void. To him, the void was essential. It was the empty stage that allowed the actors, the atoms, to move. But this was fiercely opposed by Aristotle, who famously declared that nature abhors a vacuum. His logic was that in a true void, with nothing to offer resistance, an object would move infinitely fast, which he deemed absurd. For Aristotle, space was a plenum, filled everywhere. There were no gaps. His view was so persuasive that it dominated Western thought for nearly 2,000 years. The idea of a true emptiness was considered a flaw in logic. For centuries, this was the accepted truth. But science is a story of challenging accepted truths. The tide began to turn in the 17th century. The scientist Evangelista Torricelli took a long glass tube, sealed at one end, filled it with mercury, and inverted it into a dish of mercury. The column fell, but only to a certain height. Above the mercury, in the sealed end of the tube, was a space. A space with nothing in it. This was the first artificially created sustainable vacuum. It proved that emptiness could exist. Aristotle was wrong. This discovery opened the floodgates. Scientists began to build better vacuum pumps, exploring the properties of this newfound nothingness. They discovered sound could not travel through it. They learned that objects in a vacuum fall at the same rate, regardless of mass. This was the birth of the classical vacuum a volume of space containing no matter. It was passive, featureless, and truly empty. The silent, inert stage for the laws of physics. If you could pump every single particle out of a box, what remained would be absolute nothing. Zero energy, zero activity. This idea is intuitive. It makes sense. Removing everything should leave nothing. And for a long time, this definition was perfectly adequate. But as scientists began peering into the realm of the very small, they found the old rules no longer applied. Their quest to understand the atom would force them to completely redefine the very concept of empty space. The quiet stage of the classical vacuum was about to be revealed as a place of unimaginable activity. The quantum revolution. Fields fill the void. The shift in our understanding of the vacuum began with the birth of quantum mechanics. In the early 20th century, physicists were struggling with the atom. According to classical physics, an orbiting electron should radiate away its energy and spiral into the nucleus in a fraction of a second. But atoms were stable. Something was deeply wrong with the old theories. The solution came in stages. First, the idea that energy comes in discrete packets, or quanta. The next, even bigger step, was the realization that the universe is better described not as tiny particles, but as being filled with fields. This is a crucial concept, so let's break it down slowly. Think of a magnetic field. You can't see it, but you know it's there. It's a property of space itself. Quantum field theory proposes that everything is a field. There is an electron field that permeates all of space-time, a photon field for light, and a field for every other fundamental particle. In this view, what we perceive as a particle is simply a localized vibration in its corresponding field. Imagine a perfectly still, flat lake. That's the field in its resting state. Now, if you tap the surface, a ripple spreads out. That ripple is the particle. It's not a separate thing from the lake, it's a behavior of the lake. The universe, then, is a collection of these fundamental fields, all overlapping and interacting everywhere. This brings us back to the vacuum. If the universe is made of fields, What does it mean to create a vacuum? You can remove the asterisk particles from a box. You can smooth out all the ripples on the lake. But you can't remove the lake itself. You can't remove the fields. They are the fabric of reality. So, a asterisk quantum vacuum asterisk is not absolute nothingness. It is the state where all of these quantum fields are in their lowest possible energy state. It's the fields at rest. It's the lake when it's as calm as it can possibly be. But here is the critical twist that lies at the heart of the quantum vacuum. The fields can never be perfectly still. They can never have exactly zero energy. Even in their lowest energy state, there is an inherent, unavoidable jitter. The quantum vacuum, the emptiest possible space, is constantly fluctuating. The reason for this lies in one of the pillars of quantum mechanics, the Heisenberg uncertainty principle. The engine of nothing, zero-point energy and uncertainty. Werner Heisenberg's uncertainty principle is one of the most famous ideas in physics. It states that you cannot simultaneously know with perfect precision both the position and the momentum of a particle. It's not a limitation of our tools, it's a fundamental fuzziness to reality at the quantum level. Now, let's apply this principle not to a particle, but to a quantum field. A field has two related properties: its value at a point, the height of the water in our lake analogy, and the rate at which that value is changing, the momentum of the water. The uncertainty principle, when applied to fields, says you cannot know both of these with perfect precision at the same time. If you could say, at this exact point, the field's value is perfectly zero and its rate of change is perfectly zero, you would be violating the uncertainty principle. Nature forbids this. A field cannot be perfectly flat and perfectly still simultaneously. This means that even in a complete vacuum, when the fields are in their ground state, they must continue to fluctuate. They are locked in a perpetual dance, unable to ever come to a complete rest. The surface of our quantum lake is always shimmering with tiny, impossibly fast ripples. This unavoidable, minimum amount of energy is called asterisk zero-point energy, ZPE, asterisk. Even if you could cool a system to absolute zero, this quantum motion would remain. These fluctuations are often described as asterisk virtual particles. This is a slightly misleading term, but a useful shorthand. They are not real particles we can directly observe. Instead, they are fleeting manifestations of the vacuum energy. For incredibly short moments, a bit of energy can be borrowed from the vacuum to create a particle-antiparticle pair, like an electron and a positron. They exist for an infinitesimal fraction of a second before they annihilate each other, paying back their energy debt. The quantum vacuum, then, is a roiling foam of these virtual particles, constantly popping into existence and disappearing. The physicist Paul Dirac, one of the theory's pioneers, offered an early picture of this, imagining the vacuum as an infinite sea of negative energy from which electron-positron pairs could be pulled. Though our modern description has evolved, the core idea of an active vacuum remains. But is this just a story we tell to make the equations work? Or is there physical proof that this energy of empty space is real? As it turns out, we can measure its effects directly. Proof we can touch, the observable effects. For a scientific theory to be accepted, it must make testable predictions. The idea of a vacuum filled with a seething ocean of virtual particles is so strange that it demands extraordinary evidence. And that evidence exists. The most famous demonstration is the asterisk Casimir effect. Predicted by Hendrik Casimir in 1948, the experiment is, in principle, remarkably simple. Take two perfectly flat, uncharged mirrors and place them in a perfect vacuum, just a few nanometers apart. Classically, nothing should happen. But that's not what we observe. Instead, a mysterious force pushes the two plates together. This force has been precisely measured, confirming the prediction with remarkable accuracy. Where does this force come from? It comes from the vacuum itself. Outside the plates, vacuum fluctuations of all possible wavelengths can exist. But the tiny space between the plates constrains them. Only fluctuations with wavelengths that fit neatly between the plates are allowed. Longer wavelengths are excluded. The result is that there is more vacuum energy pushing on the outside surfaces of the plates than on the inside surfaces. This net pressure pushes the plates together. The Casimir effect is the vacuum pushing on things. It is tangible proof that empty space has energy. But the evidence does not stop there. At the coldest temperatures imaginable, helium presents a quiet puzzle. According to classical physics, at absolute zero, all atomic motion should cease, and everything should solidify. But under normal pressure, liquid helium refuses to freeze, no matter how cold it gets. The reason is zero-point energy. Even at absolute zero, the uncertainty principle demands that the helium atoms retain a small amount of motion. This residual jiggling is just enough to prevent the atoms from locking into a solid crystal. The very existence of liquid helium at absolute zero is a direct consequence of the energy of the vacuum. There are even more subtle effects. The energy levels of electrons in atoms are not quite what simple quantum theory predicts. An effect known as the Lamb shift shows that the interaction of an atom's electrons with the vacuum fluctuations causes a tiny shift in their energy. This shift has been measured with exquisite precision and matches the predictions perfectly. The energy of the vacuum leaves its fingerprint on every single atom. So, the quantum vacuum isn't just theory. It's a physically real entity with measurable consequences. But its influence isn't just confined to the microscopic world. These tiny, fleeting fluctuations are believed to be responsible for the grandest structures we see in the cosmos today. Cosmic consequences and the great unsolved mystery. The influence of the quantum vacuum extends from the unimaginably small to the unimaginably large. Many cosmologists believe that every star and galaxy owes its existence to the random jitters of empty space moments after the Big Bang. According to the theory of cosmic inflation in the first sliver of a second of its existence, the universe underwent a breathtakingly rapid expansion. Now, imagine the quantum vacuum during this period. Just like today, it was filled with tiny quantum fluctuations. Normally, these would average out to nothing. But during inflation, as space itself stretched at an exponential rate, these microscopic quantum fluctuations were stretched along with it. Tiny, subatomic variations in energy were blown up to astronomical proportions. When inflation ended, these magnified fluctuations became the seeds for all structure. Regions of space that, by pure quantum chance, had a slightly higher energy density became regions with slightly stronger gravity. Over billions of years, these denser regions pulled in matter, forming the first stars and galaxies. We can actually see a snapshot of these primordial fluctuations imprinted on the cosmic microwave background, the faint afterglow of the Big Bang. The arrangement of galaxies across billions of light years may be nothing more than a magnified image of random quantum noise. This all seems to fit together beautifully. But there is a dark cloud hanging over this picture. It's arguably the biggest single problem in fundamental physics, a discrepancy so colossal it has been called the worst theoretical prediction in the history of physics, and given the name, the vacuum catastrophe. The problem is this. When physicists use quantum field theory to calculate the total energy contained within the vacuum, they get a ridiculous answer. The theoretical energy density of the vacuum comes out to be somewhere between 50 to 120 orders of magnitude larger than what we actually observe. If the observed energy of the vacuum were a single grain of sand, the theoretical prediction would be more than the mass of the entire observable universe. This energy is so enormous that it should have either curled the universe into a tiny ball the instant it was born, or blown it apart so violently that no structures could ever have formed. And yet, here we are. We observe that the universe's expansion is accelerating, driven by a mysterious force called dark energy, which appears to be a property of space itself. But the measured value of this vacuum energy is tiny. This is the catastrophe. Our best theory of the small predicts a vacuum energy that is huge. Our best theory of the large observes a vacuum energy that is small. Why is the actual value so much weaker than the theory says it should be? Is there some unknown principle that cancels almost all of this energy? Nobody knows the answer. It is one of the greatest unsolved mysteries in science. It tells us that despite all our progress, there is something profound about the nature of nothing that we have yet to comprehend. So, we have journeyed from the classical idea of a featureless void to the quantum picture of a seething, energetic sea. We started with Aristotle's belief that nature abhors a vacuum and arrived at the modern understanding that the vacuum is, in many ways, one of the most fundamental things in the cosmos. We saw how the Heisenberg uncertainty principle forbids a state of perfect stillness, demanding that space must shimmer with zero-point energy. We saw how this energy manifests as a chaotic foam of virtual particles, and how this isn't just fantasy. The Casimir effect shows us the force of the void. The refusal of liquid helium to freeze is a constant reminder of the quantum jiggle. And zooming out, we saw how these tiniest of fluctuations, stretched by the early universe, may have become the very seeds of creation. The largest structures in the universe might just be a ghostly imprint of the quantum world. But this journey has also led us to the edge of our knowledge, to the vacuum catastrophe, the colossal mismatch between prediction and observation. This great mystery reminds us that science is not a finished book of facts, but a continuing story of exploration. The simple idea of nothing has proven to be one of the richest and most important concepts in all of science. It's an engine of creation, a source of measurable force, and the keeper of physics' greatest secret. The next time you look up at the night sky, at the vast emptiness between the stars, remember that you are not looking at nothing. You are looking at the dynamic, powerful, and mysterious heart of everything. Why empty space is secretly pushing on you. For a long time, we thought we knew what nothing was. A perfect vacuum, a space with no particles, no air, no light. An absolute and featureless void. It was the background, the quiet stage on which everything else happened. But what if that understanding was incomplete? What if that nothingness is filled with a quiet, shimmering energy? What if emptiness is not empty at all, but a sea of invisible things, appearing and disappearing faster than we can imagine? And what if that sea is gently, but constantly, pushing on everything in the universe, including you? It sounds like a quiet contradiction. How could a perfect vacuum, the definition of nothing, create a real, measurable force? And yet, it is a proven part of our reality. It is a discovery that quietly changes our most basic idea of what it means for a space to be empty. It suggests the universe is far stranger and more connected than we once believed. The story of how we found this secret push from the void is a journey to the heart of reality itself, to a place where the line between something and nothing begins to fade. The old picture of nothing. To understand how strange this idea is, we first have to go back in time, to a world that was unsettled by the idea of nothing. For most of human history, a true vacuum, a space with no matter at all, was not just seen as unlikely, it was considered impossible. This idea was championed most famously by the ancient Greek philosopher Aristotle. He argued that the universe was a plenum, a space completely filled with substance. He could not imagine a void because, to him, objects moved by pushing aside what was already there. In a true void, what would stop an object from moving at infinite speed? To Aristotle, the thought itself seemed to break the laws of nature. His conclusion was simple. Nature abhors a vacuum. This phrase, horror vacui, was not just science. It became a philosophical mantra that shaped Western thought for nearly 2,000 years. To challenge it was to challenge an accepted truth. The universe, it was believed, was filled with an invisible substance, an ether, leaving no room for true emptiness. The first small crack in this old worldview appeared in the 17th century. In 1643, an Italian physicist named Evangelista Torricelli, who had studied with Galileo Galilei, was working with mercury. He filled a long glass tube with the liquid and inverted it into a basin of more mercury. The column of mercury in the tube dropped, leaving a space at the sealed top. What was in that space? Air could not have entered. Torricelli made a radical suggestion. The space was empty. He had created the first man-made vacuum. He argued that the mercury was held up not by a fear of emptiness, but by the weight of the atmosphere pressing down on the basin outside. This was a quiet but profound shift in thinking. The French scientist Blaise Pascal took this idea further, having the experiment repeated at different altitudes. The height of the mercury changed, confirming it was air pressure, not Hoover vacui, that governed the effect. But the most striking demonstration came from a German scientist named Otto von Guericke. In 1654, he created two large copper hemispheres, now called the Magdeburg hemispheres. He fit them together and, using an air pump he had invented, removed the air from inside. He then attached teams of horses to each side and had them pull. Even with the strength of 30 horses, they could not separate the hemispheres. But when von Guericke simply opened a valve and let the air rush back in, they fell apart on their own. The demonstration was clear. It was not something inside holding them together, but the force of the outside atmosphere pushing on the vacuum within. With that, the classical idea of the vacuum was born. It was a physical reality, a passive, inert, and fundamentally empty space. It was a box with nothing in it. This simple picture would remain the common sense view for the next 250 years. It made perfect sense. How could nothing do anything? The answer, it turned out, was hiding in a new kind of physics that was about to rewrite the rules of reality itself. The quantum revolution. A crack in the emptiness. The 20th century began, and with it came quantum mechanics. This new science was a journey into the strange, microscopic world of atoms and particles, a realm where the comfortable rules of our world no longer applied. And one of the first casualties of this quiet revolution was our idea of nothing. The peaceful void of classical physics was about to be revealed as a place of subtle, but constant, activity. The seeds of this change were planted by one of the most well-known ideas in science, the Heisenberg uncertainty principle. In its common form, it says you cannot know both the exact position and the exact momentum of a particle at the same time. But another version of this principle deals with energy and time. This version says that you cannot know the exact energy of a system for an infinitely small moment of time. There is always a fundamental uncertainty. Nature allows for a kind of energy borrowing, as long as the loan is paid back almost instantly. The shorter the time, the more energy can be borrowed from the void and then returned. Now, let's apply this to our empty vacuum. Classically, its energy is zero. It's empty. But the uncertainty principle suggests this cannot be true. If the energy were exactly zero, for any length of time, we would know its energy with perfect certainty. This would violate the rule. The consequence is subtle, but mind-bending. The energy of any point in space, even in a perfect vacuum, can never be truly zero. It must always fluctuate. This baseline, non-zero energy is known as zero-point energy. It is the minimum energy that any small patch of space is allowed to have. This is where the picture grows stranger still. According to quantum field theory, the universe is filled with invisible fields. An electron field, a photon field, one for every particle we know. A particle, like an electron, is simply a localized vibration, a ripple in its field. So what happens to these fields in a vacuum? Our old picture would say the fields are perfectly still. But the uncertainty principle does not allow this. The fields must always be quivering with these zero-point fluctuations. From this simmering quantum foam, pairs of virtual particles and their antimatter counterparts quietly appear, exist for a short time, and then annihilate each other, returning their borrowed energy. An electron and a positron, a quark and an antiquark, flash into being and then vanish. This is not a metaphor. The vacuum of space, the most profound nothing we can imagine, is in fact a constant, shimmering dance of countless virtual particles. The classical void was passive. The quantum vacuum is alive. For a long time, this was a fascinating but abstract idea. These virtual particles seemed like ghosts in the machine of reality. How could you ever prove that this invisible sea of energy was real? The answer would come not from looking at the vast emptiness of space, but by seeing what happened when you tried to take some of that emptiness away. The proof, the Casimir effect. The year is 1948. The Dutch physicist Hendrik Casimir is at the Philips Research Labs, working on a separate problem about the forces between molecules. As the story goes, during a walk with the great physicist Niels Bohr, Casimir mentioned how difficult his calculations were. Bohr suggested he might think about it in terms of vacuum energy fluctuations. Taking this advice, Casimir's mind took a creative leap. He began to wonder, if this sea of virtual particles is real, what would happen if you took two perfectly flat, uncharged metal plates and placed them incredibly close together in a perfect vacuum? His reasoning was as elegant as it was profound. Imagine our two metal plates, floating in the quantum vacuum. This vacuum is filled with virtual photons of all possible wavelengths, flashing in and out of existence. Now, consider the space outside the plates. Out there, virtual photons of every conceivable wavelength can appear. But what about the tiny gap between the two plates? Here, the situation is different. The plates create a boundary. Like a guitar string that can only vibrate at specific frequencies that fit between its ends, the space between the plates can only host virtual photons whose wavelengths fit neatly into the gap. Any virtual photon with a wavelength longer than the distance between the plates simply cannot form in that space. This creates a subtle imbalance. The number of virtual photon modes, and thus the number of tiny pushes, on the outside surfaces of the plates is now greater than the number of modes on the inside surfaces. This difference in the density of vacuum fluctuations creates a pressure differential. There is more pressure from the outside vacuum pushing the plates together than there is from the inside vacuum pushing them apart. The result is a net, measurable force, pushing the two plates toward each other. This is the Casimir force. It is a pure quantum mechanical force, born directly from the fabric of empty space. It is the proof that the vacuum is not nothing. For years, Casimir's prediction was just that, a theoretical curiosity. The predicted force was incredibly tiny and difficult to measure. Definitive evidence had to wait for technology to catch up. In 1997, an experiment of remarkable precision, led by physicist Steve Lamoureux, managed to measure this tiny force using a sensitive device called a torsion pendulum. He brought two metallic surfaces within microns of each other, and just as Casimir had predicted, a force appeared from the vacuum, pulling them together. The measurements matched the theory, providing a landmark confirmation of the effect. The secret push of empty space was finally measured. It was real. And yet, scientific understanding continues to quietly refine itself. More recently, in early 2026, an experiment offered an even more direct look into this hidden world. Using the star detector at Brookhaven National Laboratory, physicists collided heavy ions to generate incredibly strong electromagnetic fields. From these fields, they observed pairs of quarks and antiquarks emerging directly from the quantum vacuum, a process triggered by the collision's energy. Crucially, the spin of these newly real particles was aligned in a way that directly reflected the properties of the virtual particles from which they came. This was not a measurement of a secondary force like Casimir's, but a direct observation of particles being born from the vacuum's fluctuations, carrying information from their brief, virtual existence into the real world. It was a more direct window into the secret life of nothingness than ever before. This journey, from a simple idea to a subtle measurement, and then to an even deeper observation, is how science works. If this kind of quiet exploration into the fabric of reality helps you unwind, consider subscribing to the channel. We have so much more of the universe to uncover together. Harnessing the void, the implications. The confirmation of vacuum energy was more than just a victory for a strange prediction. It showed that the vacuum is an active participant in the cosmos. This has opened a world of challenges and possibilities, from the smallest technologies we can build to the fate of the universe itself. First, on the nanoscale. For engineers building tiny machines with moving parts smaller than a human hair, the Casimir effect is a constant reality. At these microscopic scales, the gentle push of the vacuum can become the dominant force, causing tiny components to get permanently stuck together. For years, nanotechnologists have had to design around this quantum stickiness. But what if, instead of fighting it, we could control it? Scientists are now exploring ways to engineer the Casimir force. In a stunning breakthrough, researchers have even shown a repulsive Casimir effect, making the vacuum push objects apart instead of pulling them together. Imagine nanoscale parts that levitate without contact, held aloft by the engineered energy of the void. The implications become even more profound when we consider chemistry. Scientists have discovered that if you place a molecule inside a tiny optical cavity, you can change the rules. By confining the vacuum fluctuations around the molecule, you can alter its fundamental energy levels, changing how it reacts. We could, in principle, use the engineered vacuum as a new kind of catalyst, transforming chemistry not by adding substances, but by manipulating the void. But the influence of the vacuum's energy does not stop at the nanoscale. It stretches out to the entire cosmos. One of the greatest mysteries in modern physics is dark energy. Observations have shown that the expansion of the universe is accelerating. Something is pushing space itself apart. The prime suspect is the energy of the vacuum itself. It is a beautiful and elegant idea, but it comes with a quietly humbling problem. A puzzle so profound it has been called the worst prediction in all of physics. When physicists try to calculate the theoretical energy of the vacuum, the number they get is enormous. 10 to the power of 120 times larger than what we actually observe. This disagreement, the largest in the history of science, tells us that while the vacuum has energy, we are missing a fundamental piece of the puzzle that connects the quantum world to the cosmos. Finally, and most speculatively, if the vacuum can be engineered to push and pull, could we use it to propel a spacecraft? This is the realm of distant ideas, but it is grounded in real physics. Concepts for propellantless propulsion systems exist, which aim to push off the quantum vacuum. The Casimir effect provides a known, physical way to create regions of negative energy density, a requirement for some of these exotic ideas. Learning to sail that sea, however far away it may seem today, represents one of the quiet aspirations of our species. From nanomachines to the fate of the universe, the secret push of empty space is everywhere. The new emptiness. We began with a simple picture of emptiness, a silent, absolute nothing. We saw how that idea was first challenged by pioneers like Torricelli, who dared to create a pocket of nothing and found it was the something of the atmosphere that rushed in. This gave us the classical vacuum, a sterile, empty stage. But then, the quantum revolution changed that stage completely. It took our concept of a placid void and replaced it with a vision of unimaginable, yet subtle, energy. The uncertainty principle declared that perfect nothingness is a physical impossibility. Quantum field theory painted a picture of this new emptiness, a shimmering ocean of energy fields, giving birth to and then swallowing an infinite storm of virtual particles. This was not just a theory. It was a testable prediction. Hendrik Casimir's thought experiment showed how to unmask this hidden energy. He realized that by giving emptiness boundaries, we could force it to reveal itself. A real force would emerge, a push generated not by matter or charge, but by the very structure of the vacuum itself. When delicate experiments finally measured that tiny force, and later, when the birth of particles from the void was directly observed, it was a moment of profound revelation. The push was real. The vacuum energy was real. The ghosts in the machine were tangible. Today, we know that this effect is not just a laboratory curiosity, it is a fundamental feature of nature. It is a nuisance for the nanotechnologist, a potential tool for the quantum engineer, and a quiet clue for the cosmologist trying to understand the universe. The story of the vacuum's energy is a story of how challenging our most basic assumptions can lead to extraordinary discoveries. It teaches us that the universe is under no obligation to make sense to our intuition. So the next time you look at what seems like empty space, remember what is truly there. It is not just nothing. It is a dynamic, shimmering sea of hidden energy, a quantum foam where particles are born and die in the blink of an eye. Its gentle push, a force from nothing, is a constant and powerful reminder of the strange, beautiful rules that govern our reality. And it suggests, once and for all, that even in the most profound emptiness, the universe is still quietly at work. The strange emptiness pushing our universe to its end. For as long as we have looked to the heavens, the universe has seemed eternal. A vast, unchanging architecture of galaxies and stars, bound by the familiar and relentless pull of gravity. We see the light from a billion galaxies, each a city of stars, and assume this cosmic metropolis will endure. There is a sense of permanence in the steady glow of the Milky Way, a feeling that the grand design of the cosmos is built to last. This magnificent view, however, is a fleeting one. It is a beautiful, temporary state in a cosmic story whose final pages describe a future of unimaginable emptiness and cold. Because lurking in the absolute nothingness between these galaxies, in the sterile void of intergalactic space, is a strange and invisible energy. A kind of anti-gravity that is not pulling the universe together, but quietly, inexorably, pushing it apart. This presence is causing the expansion of the universe to accelerate, driving galaxies away from each other at ever-increasing speeds, destining our cosmos for a cold, dark, and lonely end. This is a story of how the vacuum of space itself, the very concept of nothing, seems to hold the key to everything. It is a story of a quiet discovery that turned cosmology on its head, of a supposed blunder made by one of history's most famous scientists that turned out to be eerily prescient, and of one of the most profound mismatches between theory and reality in the history of science. This is the story of dark energy, the strange emptiness that is shaping the ultimate fate of everything that has ever been or ever will be. Our deepest understanding of physics suggests this force shouldn't exist, at least not in the way we observe it, yet its effects are undeniable. We are living in a brief, special moment of cosmic history, and the evidence of our universe's final act is written across the sky, waiting for us to decipher it, before it vanishes from view. The universe is being pushed apart by something we cannot see, a quiet presence that inhabits the void. And perhaps the most unsettling part of this cosmic mystery is what happens when we try to explain it. Our best, most successful theory of the subatomic world, quantum field theory, predicts that this energy should exist. But it predicts that it should be so powerful, so catastrophically strong, that it should have torn our universe to shreds in the first fraction of a second of its existence. Our observations show a gentle, accelerating expansion, while our theories predict an event of incomprehensible scale. This discrepancy, a quiet chasm between what we see and what we calculate, is sometimes called the vacuum catastrophe, and it has been described as the worst theoretical prediction in the history of physics. We are faced with two possibilities. Either our understanding of the universe is fundamentally incomplete, or we are missing a crucial piece of the puzzle. A piece that explains why the nothingness of space is so surprisingly calm. To understand how we arrived at this precipice of knowledge, we must first go back to a time when our picture of the cosmos was much simpler, and, as it turned out, entirely different. The old story, a universe in balance. For most of human history, the universe was a place of serene stability. To the ancients, the stars were fixed points of light on a celestial sphere, unchanging and eternal. This idea of a static cosmos was so ingrained in our thinking that it persisted well into the 20th century, shaping the very foundations of modern cosmology. The first great architect of our understanding of cosmic forces was, of course, Isaac Newton. His law of universal gravitation, formulated in the late 17th century, described a universe governed by a single, relentless force. Every object, from an apple to the moon, pulled on every other object. Gravity was the master of the cosmos, a force that always attracts, never repels. When applied to the universe as a whole, Newton's theory had a startling implication. If the universe were finite, gravity should cause everything to collapse together into one giant mass. The only way to avoid this cosmic pile-up was to imagine an infinite universe, where every star was pulled equally in all directions by an infinite number of other stars, creating a precarious, delicate balance. This picture was revolutionized in the early 20th century by Albert Einstein. His theory of general relativity, published in 1915, offered a new vision. In Einstein's universe, gravity was not a force transmitted across space, but an intrinsic property of space and time itself. He described a four-dimensional fabric called space-time, and massive objects like stars and galaxies warp this fabric. What we perceive as gravity is simply the motion of objects following these curves, like a marble rolling along a bent path on a stretched rubber sheet. But when Einstein applied his powerful new equations to the universe as a whole, he encountered the same problem as Newton. His own theory predicted that a universe filled with matter should be dynamic. It should either be expanding or contracting. The immense gravitational pull of all the matter in the universe should cause spacetime itself to curve inwards, pulling everything together. A static, eternal universe, which was the prevailing astronomical wisdom of the day, was not possible under his original equations. This result troubled Einstein. It seemed his elegant theory failed to describe the universe he thought he lived in. To resolve this, he introduced a new term into his equations, something he called the cosmological constant, represented by the Greek letter lambda, lambda. He envisioned this as an intrinsic energy of space itself, a kind of anti-gravity that would create a repulsive force, pushing space-time outward to perfectly counteract the inward pull of gravity. With this addition, he could make his model of the universe static, balanced on a cosmic knife's edge. But science moves on. In 1929, the American astronomer Edwin Hubble made a discovery that would change everything. By observing the light from distant galaxies, he noticed it was consistently shifted towards the red end of the spectrum. This phenomenon, known as redshift, is a cosmic equivalent of the Doppler effect. Just as the pitch of a siren drops as it moves away, the wavelength of light from a receding object stretches, becoming redder. Hubble found that the farther away a galaxy was, the greater its redshift, and therefore the faster it was moving away from us. The conclusion was inescapable. The universe was not static. It was expanding. The space between galaxies was stretching, carrying them along for the ride. Hubble's discovery removed the foundation for a static universe model. Einstein's motivation for inventing the cosmological constant had vanished. Physics lore tells us that Einstein later called the introduction of this term his biggest blunder, an unnecessary complication to his otherwise beautiful equations. With the cosmological constant set aside, a new story of the cosmos emerged. The universe began in an incredibly hot, dense state, the Big Bang, and has been expanding and cooling ever since. This expansion, however, was expected to be slowing down. The universe was like an object thrown upwards from the ground. While it starts fast, Earth's gravity constantly pulls on it, slowing it down. Similarly, the mutual gravitational attraction of all the matter in the universe was expected to act as a brake on the expansion, causing it to decelerate over billions of years. The ultimate fate of the cosmos then became a question of density. If the amount of matter in the universe was above a certain critical value, gravity would eventually win. The expansion would slow, halt, and reverse, leading to a big crunch, a final collapse where the universe would end as it began. If the density was below this critical value, gravity would not be strong enough. The expansion would slow but never stop, and the universe would expand forever, growing colder and darker in a scenario known as the Big Freeze. For decades, cosmologists worked to measure the cosmic expansion rate and take a census of all the matter in the universe to determine which of these two fates awaited us. They were confident they understood the rules. Gravity was in charge. No one was prepared for the discovery that the rules themselves were about to change completely. The shocking discovery: the rules have changed. By the late 1990s, cosmology felt like it was on the verge of a major breakthrough. Two independent teams of astronomers were engaged in a quiet, intense effort to achieve a long-sought goal: to precisely measure the deceleration rate of the universe. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were poised to pin down the cosmic density and finally determine our ultimate fate. Their method was conceptually simple but technically demanding. They needed to measure both the distance to and the speed of extremely remote objects. To do this, they used a special kind of stellar explosion known as a Type Ia supernova. These supernovae are what astronomers call standard candles. They are not just any explosion. They occur when a white dwarf star, the dense remnant of a star like our Sun, accretes too much matter from a companion star. When the white dwarf reaches a very specific mass, about 1.4 times the mass of our Sun, it triggers a runaway thermonuclear reaction, and the entire star is consumed in an explosion of standardized brilliance. Because they all begin from the same mass, their intrinsic brightness is remarkably consistent. This consistency is what makes them such powerful cosmological tools. If you imagine a row of identical light bulbs stretching off into the distance, the farther away a bulb is, the dimmer it appears. By measuring its apparent faintness, you can calculate its distance. Type Ia supernovae are the universe's standard light bulbs. By finding these explosions in distant galaxies and measuring how bright they appear, astronomers could determine their distance from us with great accuracy. At the same time, they measured the supernova's redshift. As the universe expands, it stretches the wavelengths of light traveling through it. Light from a distant supernova that has traveled for billions of years will be redshifted by an amount that corresponds to how much the universe has expanded since the light began its journey. The plan was to plot these two measurements against each other. Apparent brightness, which indicates distance, versus redshift. By comparing nearby supernovae to very distant ones, the teams could chart the history of cosmic expansion. If the universe's expansion was slowing down due to gravity, as everyone expected, the most distant supernovae should appear brighter than they would in a constantly expanding universe. This is because, in a decelerating universe, the expansion was faster in the past. To reach a given redshift, the light from a distant supernova wouldn't have had to travel quite as far. A shorter distance means a brighter supernova. The teams painstakingly gathered their data, searching for the faint, fleeting light of these exploding stars billions of light years away. As the data points started to accumulate on their graphs, something was deeply strange. The distant supernovae were not brighter than expected, they were dimmer. Consistently, systematically, they were about 25% dimmer than they should have been in a universe where gravity was slowing things down. The implication was so bizarre that both teams initially assumed there was an error. They rechecked their calculations. Perhaps some unforeseen dust in intergalactic space was absorbing some of the light, making the supernovae appear fainter and thus farther away. But the dimming was consistent across different wavelengths of light, which is not how dust behaves. Perhaps distant supernovae were intrinsically different from nearby ones. This idea, too, was carefully scrutinized and found to be unlikely. After months of ruling out every possible source of error, both teams were forced to confront the same quiet, startling conclusion. The distant supernovae were dimmer because they were farther away than any of the existing models predicted. For them to be that far away, the expansion of the universe couldn't have been slowing down. In fact, over the last several billion years, it must have been speeding up. This was the moment that turned cosmology on its head. It was as if you had tossed a ball into the air, and instead of slowing down and falling back, it suddenly began to accelerate upwards, faster and faster. The discovery, announced in 1998, was a profound revelation. It meant that for the last 5 billion years or so, some mysterious, repulsive presence has been overwhelming the familiar pull of gravity on cosmic scales. The universe was not on a path to a big crunch or even a gentle big freeze. It was being pushed apart. The Nobel Prize in Physics was awarded to Perlmutter, Schmidt, and Rees in 2011 for this work, a testament to its deep impact on our understanding of the cosmos. The old story was over. A new and far stranger one had to be written. Physicists had a new mission: to find the source of this cosmic acceleration. They gave it a name, a placeholder for our ignorance: dark energy. The suspect: what is dark energy? With the discovery of cosmic acceleration, the search was on to identify the cause. What was this mysterious entity, this dark energy, that made up nearly 70% of the universe's total energy budget and was actively pushing it apart? It is important to clarify what it is not. Dark energy is not dark matter. While both are invisible, they are thought to be different things with opposite effects. Dark matter is a form of matter whose gravitational pull we can detect. It clumps together, forming halos around galaxies, and its gravity helps hold those structures together. Dark energy, on the other hand, does not seem to clump. It appears to be a smooth, uniform energy spread thinly throughout the universe, and its effect is repulsive. It pushes things apart. So, what could dark energy be? The most direct and leading candidate took physicists back to Einstein's biggest blunder. Perhaps the cosmological constant, lambda, was real after all. What Einstein had invented to create a static universe and then discarded when the universe was found to be expanding, was now revived to explain why that expansion was accelerating. In this new context, the cosmological constant is interpreted as the energy of the vacuum itself, the energy of empty space. This brings us to one of the most foundational concepts in modern physics: the idea that nothing is not actually empty. According to quantum field theory, a perfect vacuum is not an inert void. Instead, it is a seething cauldron of activity. The quantum vacuum is alive with what are called virtual particles. Due to the Heisenberg uncertainty principle, energy can be briefly borrowed from the vacuum to create a particle-antiparticle pair. These pairs, an electron and a positron, for example, flash into existence for an immeasurably short moment before annihilating each other, vanishing back into the nothingness from which they came. This quiet sea of transient particles fills all of space, giving the vacuum a non-zero energy. The existence of this vacuum energy is not just a theoretical idea. It has observable effects. One of the most famous is the Casimir effect. If you place two uncharged, parallel metal plates extremely close together in a vacuum, they will be pushed together by a tiny, but measurable, force. This happens because the space between the plates restricts the kinds of virtual particles that can appear there, while the full spectrum of particles can exist on the outside. This creates a pressure difference, and the plates are gently forced together. It is quiet experimental evidence that the energy of the quantum vacuum is real. General relativity predicts that this vacuum energy would behave in a very specific way. It would have negative pressure. For a normal gas, when you expand its volume, its pressure drops. Vacuum energy does the opposite. As space expands, the energy density stays constant, so the total energy inside the expanding volume increases. To create this new energy, the vacuum must do negative work on its surroundings. It pulls outward, helping the expansion along. In general relativity, this negative pressure creates a repulsive gravitational effect. It is a source of anti-gravity. So, we have a perfect suspect. Quantum theory predicts that empty space has energy, and general relativity predicts that this energy would have negative pressure, causing the expansion of the universe to accelerate. It seemed like a beautiful convergence of our two great pillars of modern physics. The blunder was no blunder. Einstein had been right, just for the wrong reason. But as physicists began to consider this elegant solution, they encountered one of the greatest challenges in the history of science: the cosmological constant problem, or the vacuum catastrophe. The problem arises when you try to calculate how strong this vacuum energy should be. There are two ways to get a value for it. The first is to measure it through cosmological observations. Based on the acceleration rate from the supernova data, astronomers can calculate the exact density of dark energy needed. This value is tiny, about 10 to the power of -9 joules per cubic meter. The second way is to calculate it from quantum field theory, by summing up the energies of all the virtual particles that should be flickering in and out of existence. When physicists do this, the number they get is not small. It is monstrously, absurdly large. About 10 to the power of 113 joules per cubic meter. This is not a small disagreement. It is a discrepancy of 122 orders of magnitude, a 1 followed by 122 zeros. It has been called the largest discrepancy between theory and experiment in all of science. If the vacuum energy were truly this strong, its repulsive force would be so immense that it would have instantly overcome the forces holding atoms together. The universe as we know it, with stars, planets, and people, should not exist. This is the vacuum catastrophe. It is a quiet but profound sign that our understanding is incomplete. Is dark energy something other than vacuum energy, perhaps a new, evolving energy field, sometimes called quintessence? Or is there some unknown physical principle that cancels out almost all of the predicted vacuum energy, leaving behind just the tiny residual amount we observe? Some have even speculated about a multiverse, where countless universes exist with different values for their vacuum energy, and we simply happen to live in one of the very rare ones where it's small enough for structures to form. As of today, this remains one of the deepest unsolved problems in physics. We have a suspect, the energy of the vacuum, but its theoretical profile does not match the evidence from the cosmos. The endgame: 3 possible fates. The discovery that an unknown energy is accelerating the cosmic expansion forces us to reconsider the ultimate fate of our universe. The old story was a contest between gravity and momentum. Now, with dark energy in play, the future is more uncertain and depends entirely on the true nature of this mysterious presence. The destiny of the universe hinges on a single parameter known as the dark energy equation of state, represented by the letter W. The parameter W is the ratio of dark energy's pressure to its energy density. Its value determines how the density of dark energy changes as the universe expands, and thus dictates the future. Cosmologists are working to measure W with ever-increasing precision, as its value points toward one of three possible final acts for our universe. Scenario 1. The Big Freeze, or heat death. This is the most widely accepted scenario, consistent with dark energy being Einstein's cosmological constant. In this case, W is exactly equal to -1. This means the density of dark energy remains constant for all time. As space expands, more energy of the vacuum is created, keeping the density the same. The repulsive force is therefore steady and unchanging. In this future, the accelerating expansion continues. For billions of years, the changes would be subtle. But the relentless push of dark energy would eventually dominate over gravity on increasingly smaller scales. In about 100 to 150 billion years, all galaxies outside our own local group will have been pushed beyond our cosmic event horizon. Their light will no longer be able to reach us. For any future observer in our galaxy, the universe beyond our local island of galaxies will become completely dark and empty. The local group itself will eventually merge into one giant galaxy. Within this super galaxy, the era of star formation will slowly come to an end as the clouds of gas and dust are used up. The longest-lived stars, the small red dwarfs, will shine for trillions of years, but eventually, they too will fade. What follows is an almost unimaginably long period known as the degenerate era. The universe will be a graveyard of stellar remnants, black holes, neutron stars, and cold white dwarfs. Over even longer timescales, perhaps 10 to the power of 36 years, some theories suggest that protons themselves may decay, causing atoms to dissolve into a sea of radiation. Finally, in the black hole era, the only large objects left will be black holes. These too are not eternal. They slowly evaporate through Hawking radiation. Over a period up to 10 to the power of 100 years, they will all radiate away their mass and vanish. At the end of this process, the universe will enter its final state, heat death. It will be a cold, dark, and utterly empty void, populated only by a sparse gas of photons and elementary particles, all at a temperature infinitesimally close to absolute zero. All activity will cease. Time itself will lose its meaning. This is the Big Freeze, a future of eternal, unchanging quiet. Scenario 2. The Big Rip. This is a far more dramatic end, and it would occur if dark energy is something more potent than a cosmological constant. This scenario happens if the parameter, W, is less than -1. A hypothetical form of dark energy with this property is called phantom energy. If dark energy is phantom energy, its density would increase as the universe expands. The more space expands, the more powerful the repulsive force becomes, leading to a runaway feedback loop of hyperacceleration. The timeline for such an event would be startlingly fast and destructive. According to some theoretical models, about a billion years before the end, the repulsive force of phantom energy would become strong enough to unbind clusters of galaxies. About 60 million years before the end, the fabric of individual galaxies would unravel. 3 months before the final moment, the acceleration would be powerful enough to strip planets from their stars. 30 minutes before the end, the Earth itself would be pulled apart. In the final fraction of a second, the force would grow to near infinite strength. It would overwhelm the electromagnetic forces holding molecules and atoms together. Then, in the last moments, it would overpower even the strong nuclear force. Atomic nuclei would be torn apart. The universe would end not as a cold, empty place, but in a final singularity where every fundamental particle is ripped apart from every other. The very fabric of space-time would be undone. Current measurements of W are frustratingly close to -1, making it difficult to distinguish between the big freeze and the big rip. The data allows for both possibilities, leaving our final destiny balanced on a razor's edge. Scenario 3. The Big Crunch, an echo of the past. Though largely disfavored by current evidence, there remains a slim possibility that dark energy is not constant. If it were a dynamic field that could eventually decay or even switch from repulsive to attractive, the story would change once more. In such a scenario, the accelerating expansion we currently observe would only be a temporary phase. If dark energy were to weaken, gravity would once again become the dominant force on cosmic scales. The expansion of the universe would slow, halt, and then begin to reverse. This would lead to the Big Crunch. The universe would contract, with galaxies rushing towards each other. The sky would grow brighter and hotter as the cosmic microwave background radiation is blue shifted to higher energies. In the final moments, the universe would return to a state similar to its beginning, an infinitely hot, infinitely dense singularity. Some speculative theories suggest this collapse could lead to a Big Bounce, where the universe rebounds and begins a new cycle of expansion and contraction. While the Big Crunch is now considered the least likely of the three fates, its theoretical possibility is a reminder of how much we still have to learn. Our journey into the cosmic void has led us to a place of profound mystery. We began with a universe we thought we understood, governed by the steady hand of gravity. We now find ourselves in a far stranger reality, a universe whose fate is being shaped by the energy of nothingness itself. The discovery that the universe's expansion is accelerating has, in a quiet twist of irony, resurrected Einstein's cosmological constant, transforming his biggest blunder into a prophetic insight. Yet this solution comes with its own challenge. The vast chasm between the theoretical prediction for the energy of the vacuum and its observed value, the vacuum catastrophe, remains one of the deepest signs that our fundamental understanding of physics is incomplete. We are left looking into a quiet abyss of ignorance. Is dark energy the constant energy of the vacuum, destined to drive our universe into a big freeze? Is it a phantom energy, fated to tear reality apart in a big rip? Or could it be an ephemeral force, one that might fade and allow gravity to pull everything back into a fiery Big Crunch? The answer lies hidden in the precise nature of this strange emptiness. There is a certain poignancy in our cosmic situation. We live in a special, fleeting era, a time when the universe is old enough for galaxies and stars to have formed, yet young enough that the evidence of the Big Bang and the sight of distant galaxies have not yet been pushed beyond our reach. Future observers, in the far future of our own galaxy, may look out into a completely empty sky, with no way of knowing that a vast cosmos of other galaxies ever existed. They might be trapped in a state of cosmic solitude, unaware of the universe's true scale or its dramatic origin story. We are the generation that gets to witness the full view, before the eternal night sets in. The strange emptiness pushing our universe to its end is not just a scientific curiosity. It is a fundamental aspect of our reality that defines our past, present, and future. It is a reminder that even in the absolute void, there are deep secrets to be found, and that the biggest questions about our existence are written not just in the stars, but in the silent, expanding darkness between them. How nothingness breaks all the rules of physics. For a long time, the space between things seemed to be just that, space. The silence between stars, the void in a vacuum. For centuries, even the most careful thinkers in physics saw it this way. Isaac Newton viewed space as an empty, unchanging stage where the events of the universe took place. It was the absolute, silent backdrop to everything. Even Albert Einstein, who reshaped our understanding of gravity, saw it as the calm, quiet fabric of reality itself. A well-behaved, smoothly curving sheet he called spacetime. But this was not the complete picture. Quantum mechanics, our other pillar of modern science, tells a profoundly different story. It suggests that at its smallest, most fundamental level, this nothing is a place of constant, subtle activity. A place where particles can emerge from energy and vanish in an instant, a quiet storm of potential that, according to the math, should have consequences for the entire cosmos. So, which is it? Is nothing the calm stage for reality, or is it an engine of subtle but powerful energy? This is not a small disagreement over decimal points. It is one of the largest, most profound unsolved mysteries in all of science. Our two greatest theories for describing reality offer starkly different accounts of what that reality is at its most basic level. And the answer, when it is eventually found, will change our understanding of, well, everything. We tend to think of empty space as calm and peaceful. We have been told it's nothing. But what if this nothing that fills the vastness between galaxies is actually something of immense importance? This is the story of how our two greatest theories of physics came into conflict over the meaning of empty space, and how that conflict revealed a deep question at the very foundation of our understanding of the universe. This is the story of the vacuum. The two camps, a universe divided. To understand this quiet conflict, you first had to understand the two perspectives involved. On one side, we have general relativity. This is Einstein's masterpiece. It is a theory that paints a picture of the universe on the largest of scales. Think of planets orbiting stars, stars clustering into galaxies, and galaxies moving through the cosmos. General relativity describes space and time not as a fixed background, but as a single, interwoven entity, spacetime. And this spacetime isn't rigid, it's a dynamic, flexible fabric. Imagine a heavy ball placed on a stretched rubber sheet. The ball creates a dip, a curve in the sheet. If you then roll a small marble nearby, it will follow the curve created by the ball. According to Einstein, this is gravity. Mass and energy tell spacetime how to curve, and the curvature of spacetime tells matter how to move. In this vision of the universe, the vacuum, the space between the masses, is elegant, smooth, and predictable. It can be warped and stretched, but it is fundamentally calm. For over 100 years, general relativity has passed every test we've been able to devise, from predicting the bending of starlight to confirming the existence of gravitational waves. It is, without doubt, one of the most successful scientific theories ever conceived. On the other side, we have quantum mechanics. If general relativity is the master of the large-scale cosmos, quantum mechanics is the undisputed ruler of the subatomic realm. It governs the world of the very small, the atoms, electrons, and photons that make up everything we see. But the world it describes is deeply counterintuitive. Unlike the smooth, continuous reality of Einstein, the quantum world is quantized. It comes in discrete, indivisible packets. Think of a light switch. In our everyday world, you could have a dimmer, allowing for a continuous range of brightness. In the quantum world, it is a standard switch. It is either on, or it is off. An electron in an atom cannot have just any energy. It must occupy specific energy levels, like rungs on a ladder. It can jump from one rung to another, but it can never exist between the rungs. Furthermore, quantum mechanics is a theory built on probability and uncertainty. It does not tell you where a particle is, it tells you where it might be. A particle can exist in many states at once, a concept called superposition, until it is measured, at which point it settles into one definite state. This theory describes a world that is fundamentally granular and probabilistic. And just like general relativity, it has been tested to an incredible degree of accuracy. The technologies that power our modern world, from computers to lasers, are all built on our understanding of its rules. For much of the last century, this division worked well. Physicists used general relativity for big things and quantum mechanics for small things. The two theories governed their separate domains. But there is one place in the universe where these two realms are forced to meet. One place where the macro and the micro must confront each other. And that place is the vacuum. It is the empty space that exists at both the largest cosmic distances and the smallest subatomic scales. And when our two greatest theories tried to describe it, they did not just disagree. They produced a result so profoundly at odds with observation that it has been called the worst theoretical prediction in the history of physics. The quantum view of nothing. So, what is the quantum version of nothing? If you ask a quantum physicist to look at a patch of truly empty space, a perfect vacuum, sealed off from all matter and cooled to absolute zero, they will not see nothing. They will see a place of subtle, constant activity. This is the quantum vacuum. The reason for this lies in one of the core ideas of quantum mechanics, the uncertainty principle. Formulated by Werner Heisenberg, it states that you can never know certain pairs of properties, like a particle's position and its momentum, with perfect accuracy at the same time. The more precisely you know one, the less precisely you know the other. This principle also applies to energy and time. You can never be certain that any region of space has exactly zero energy, because to be certain of its energy, you would need to observe it for an infinite amount of time. Over very short timescales, the energy at any given point in space can fluctuate. These are called quantum fluctuations. Even in the lowest possible energy state, the zero-point energy, the vacuum is alive with this simmering energy. This is not just a mathematical curiosity, it is the fundamental reality of empty space according to quantum field theory. Quantum fields permeate all of space. There is an electron field, a photon field, and a field for every other known particle. A particle is simply a localized excitation of its corresponding field, like a ripple in a pond. But even when there are no particles, the fields themselves are still there, constantly fluctuating. For a fleeting moment, these energy fluctuations can borrow enough energy from the vacuum to create a pair of particles, a particle and its antimatter counterpart. These are called virtual particles. They blink into existence, exist for an impossibly short time, and then annihilate each other, returning their energy to the vacuum. The vacuum, then, is a quiet, roiling foam of these virtual particles, appearing and disappearing in a constant, subtle dance. This may sound like a purely abstract idea, an ocean of invisible energy and fleeting particles. But the effects of this quantum vacuum are real and have been measured with incredible precision. One of the most famous examples is the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir predicted that if you place two uncharged metal plates incredibly close together in a vacuum, a force will push them toward each other. This is because the space between the plates restricts the wavelengths of virtual particles that can appear there. The space outside the plates has no such restriction. This imbalance in the fluctuations creates a pressure differential, pushing the plates together. This is not a theory. The Casimir effect has been measured in laboratories, and the results match the predictions of quantum field theory perfectly. It is direct evidence that the vacuum is not empty. It exerts a real, physical force. This same zero-point energy also subtly shifts the energy levels of electrons in atoms, an effect known as the Lamb shift, which has also been measured and confirmed. Recent experiments in early 2026 at facilities like Brookhaven's relativistic heavy ion collider have even found direct evidence of these virtual particle pairs, confirming this once theoretical concept with hard data. So, we know the quantum vacuum is real. It is a fundamental, measurable part of our universe. The nothing of empty space is, in fact, a something with real physical consequences. This leads to a simple, logical question. If the vacuum is filled with all this energy, how much energy are we talking about? This is the question physicists asked. And the answer they got did not just present a problem. It revealed a deep contradiction in our understanding of the universe. The vacuum catastrophe. This is where the story takes a quiet but dramatic turn. This is the moment when the two pillars of physics, general relativity and quantum mechanics, collide. The physicists who set out to calculate the energy density of the quantum vacuum knew the energy was real, thanks to effects like the Casimir force. The calculation, in principle, is straightforward. You take all the known quantum fields, consider all their possible modes of vibration at every point in space, and then sum up the zero-point energy for every single one of those modes. When they did this, the first answer they got was infinity. The equation suggested that every cubic centimeter of empty space should contain an infinite amount of energy. Physicists are accustomed to infinities appearing in their calculations. They usually signal that a theory is incomplete or is being applied beyond its limits. So, a more sophisticated approach was taken. They reasoned that our current theories likely break down at some incredibly high energy, the so-called Planck energy, where the effects of quantum gravity would become important. They decided to cut off their calculation at that energy scale, summing only the contributions from fluctuations up to that limit. This is a common technique in physics, a way of making a sensible prediction while acknowledging the limits of current theories. They performed the calculation again. This time, they did not get infinity. But the finite number they got was so large that it created an even greater problem. The theoretical prediction for the energy density of the vacuum was approximately 10 to the power of 113 joules per cubic meter. To put that number in perspective, if you were to take all the energy from all the stars in the entire observable universe and concentrate it into a single cubic meter, the resulting energy density would be insignificant compared to the theoretical energy of the vacuum. The predicted energy of nothing was vastly greater than the energy of everything combined. This is where general relativity re-enters the picture. According to Einstein's theory, all forms of energy are a source of gravity. Energy curves spacetime. An energy density of 10 to the power of 113 joules per cubic meter is not a small amount. It is an amount of energy so stupendous that its gravitational effect would be cataclysmic. If the vacuum truly had this much energy, the immense gravitational pull of its own energy would have caused the universe to collapse into a space smaller than an atom, less than a second after the Big Bang. The universe as we know it, vast, expanding, and filled with galaxies, should not exist. And yet, we are here. We observe the universe, and we see that it is not curled up into a tiny ball. It is, in fact, expanding. This colossal disagreement between what quantum theory predicts for the vacuum energy and what we actually observe is what physicists call the asterisk vacuum catastrophe. It is, without exaggeration, the single greatest failure of a physical theory in history. For decades, this was a difficult problem in theoretical physics. Many physicists assumed there must be some unknown principle that causes the total vacuum energy to cancel out to exactly zero. They would perform a mathematical adjustment called renormalization to reset the value and proceed with other calculations, effectively setting the problem aside. It was an unresolved issue, but one that could mostly be separated from other work. And then, in 1998, everything changed. A group of astronomers looking at distant supernovae made a discovery that brought the vacuum catastrophe back to the forefront. They found that not only was the universe not collapsing, it was not even slowing down. The expansion of the universe was accelerating. A clue from the cosmos. The discovery in 1998 was one of the most important in the history of astronomy. Two independent teams were using distant exploding stars, type Ia supernovae, as standard candles, to measure the expansion rate of the universe. These supernovae always explode with a predictable intrinsic brightness, so by measuring how faint they appear, astronomers can calculate how far away they are. By measuring their redshift, they can tell how fast they are moving away from us. The expectation was that the expansion of the universe was slowing down. Gravity, after all, is an attractive force. The mutual pull of all the matter in the cosmos should act as a cosmic brake, gradually slowing the expansion that began with the Big Bang. But that is not what they found. They found the opposite. The distant supernovae were fainter than they should have been, meaning they were farther away than predicted. The only way to explain this was if the expansion of the universe had been speeding up over the last few billion years. Something was pushing space apart. Something was acting as a form of anti-gravity, stretching the fabric of spacetime itself. Scientists gave this mysterious phenomenon a name: dark energy. Follow-up observations, especially from mapping the cosmic microwave background radiation, have confirmed this discovery with remarkable precision. The data tells us that about 68% of the total energy density of the universe is in the form of this dark energy. Another 27% is dark matter, and a mere 5% is the ordinary matter that makes up stars, planets, and us. We live in a universe dominated by components we do not fully understand. But here is the most fascinating part. All of our best evidence suggests that dark energy is a property of the vacuum of space itself. It appears to be a small, positive, intrinsic energy that exists everywhere. Its density does not dilute as the universe expands. As more space is created, more of this energy comes with it, which is why its effect has become more dominant over time. So, the vacuum does have energy. And this energy does have a gravitational effect. It is the very thing that is pushing the universe apart. Astronomers were able to measure the value of this vacuum energy. They found it to be incredibly small, about 10 to the power of -9 joules per cubic meter. Suddenly, the vacuum catastrophe was no longer a theoretical abstraction. It was a real, observational crisis. Physicists could no longer just assume the vacuum energy was zero. It wasn't. It was tiny, but it was definitively not zero. The universe itself was telling them that the vacuum had energy. But this only deepened the mystery. The problem was no longer that theory predicted a huge energy while observation suggested zero. The problem was that theory predicted a huge energy, and observation showed a tiny, non-zero energy. The discrepancy was now between two numbers. The theoretical value was about 10 to the power of 120 times larger than the observed value. That is a 1 with 120 zeros after it. To put that discrepancy into perspective, it is like measuring the diameter of our solar system and being off by the width of the entire observable universe. This is not a small error. It is a sign that we are missing something profound about how reality works. The conflict between the smooth, geometric world of Einstein and the energetic world of quantum mechanics had produced the most epic failure in the history of science. The final frontier. So, why is the prediction so catastrophically wrong? Why do our two best theories of reality disagree so profoundly? This is, without question, the biggest unsolved problem in fundamental physics, and nobody knows the answer for sure. But there are clues, and they point to the very nature of space, time, and gravity. The root of the problem seems to lie in the different ways general relativity and quantum mechanics describe the world. General relativity is a theory of a smooth, continuous fabric of spacetime. Quantum mechanics is a theory of discrete, granular fields. The two languages are different. When you try to calculate a quantum effect, vacuum energy, and plug it into a relativistic equation, for gravity, you get a result that doesn't make sense. This tells us that our theories are likely incomplete. They are both incredibly successful approximations of a deeper theory we have not yet discovered, a theory of quantum gravity. This undiscovered theory would need to unify the laws of the large and the small into a single, coherent framework. It would have to explain what spacetime is like at the tiniest possible scales, where the smooth fabric of Einstein's universe is expected to dissolve into something else entirely. What could this new theory look like? There are many ideas. String theory, for instance, proposes that the fundamental constituents of the universe are not point-like particles but tiny, vibrating strings. In some versions of this theory, through a property called supersymmetry, the contributions to the vacuum energy from different types of particles could almost perfectly cancel each other out. This could, in principle, make the vacuum energy much smaller. But so far, direct evidence for this has not been found, and the theory has not yet provided a definitive explanation for the small, non-zero value we observe. Another idea is that the immense energy of the quantum vacuum we calculate might not be the same thing that gravity responds to. Perhaps it is gravitationally inert for some unknown reason. The late physicist Roger Penrose proposed a fascinating idea that highlights the deep conflict. He argued that gravity itself might be the thing that resolves some of the strangeness of the quantum world. This suggests a feedback loop where quantum mechanics influences gravity, and gravity, in turn, polices the boundaries of quantum mechanics. What's clear is that the vacuum catastrophe isn't just a numerical error. It's a signpost, pointing toward a new frontier of physics. It tells us that the nothing of empty space is the arena where our most fundamental descriptions of reality no longer align. Solving this mystery isn't just about fixing an equation. It's about finding the next revolution in our understanding of the universe. It will require a theory that can bridge the gap between the quantum and the cosmos, one that can finally explain the true nature of space and time. We began with a simple question: what is nothing? We journeyed through Einstein's vision of a calm, geometric cosmos and into the subtle, energetic reality of the quantum vacuum. We saw how these two great pillars of science, the twin triumphs of 20th-century physics, ended up offering two incompatible descriptions of empty space. We discovered that nothing is not empty. It is a place of simmering zero-point energy, whose existence is confirmed by laboratory experiments. We then confronted the vacuum catastrophe, the moment our theories predicted that this nothing should contain enough energy to instantly collapse the universe. A prediction that is wrong by an astonishing 120 orders of magnitude. Finally, we looked to the sky and found a clue from the cosmos itself: dark energy. The accelerating expansion of the universe tells us that the vacuum does have a tiny bit of energy, a whisper of a force that is shaping the ultimate destiny of our universe. The calm of Einstein's spacetime and the activity of the quantum vacuum are not two different stories. They are two chapters of the same, unfinished book. Nothing turns out to be one of the most mysterious and poorly understood somethings in all of existence. It is the battleground where our deepest understanding of reality is tested, and it is the place we must look to find the next great leap forward. Our two greatest theories of science disagree on what reality is at its most fundamental level. Solving that mystery may be the final step to truly understanding our universe. Or it may simply show us that we have only just begun to ask the right questions. What do you think? Is there a hidden principle that resolves this enormous discrepancy? Or is there something about the nature of the void our theories have yet to grasp? Feel free to share where you're watching or listening from, and what you believe lives in the quiet, empty space between the stars. Science just found the foundation of all reality. Everything you see, the world around you, the screen you are watching this on, even your own body, it all feels solid, substantial, real. But what if all of it, everything you have ever known, is just a subtle pattern on the surface of a deep and quiet reality? For millennia, humanity has been on a journey, a kind of grand detective story to find the smallest thing that builds our world. But science is now revealing a quiet, counterintuitive truth. The foundation of all reality isn't a thing at all. It may be the emptiness in between. The story of this discovery doesn't just reshape physics. It invites us to question the nature of existence itself. The enduring mystery of the atom. Our story begins not in a modern laboratory, but in the minds of ancient Greek thinkers over 2,000 years ago. Philosophers like Leucippus and his student Democritus looked upon the world and asked a question of breathtaking simplicity. If you take an object, say, a piece of stone, and cut it in half, and then cut that half in half again, can you do this forever? Or do you eventually reach a final, uncuttable piece? They wagered on the latter. They imagined a fundamental building block of nature, a particle they called atomos, which means uncuttable. This was the first great intuitive step in our cosmic story. The idea that the staggering diversity of the world was all just a quiet rearrangement of fundamental, solid particles. It was an idea of profound elegance, but for 2,000 years, it remained just that, an idea. A philosophical dream. It wasn't until the early 19th century that this ancient dream began to take shape as a scientific theory. The English chemist John Dalton, studying how elements combine, noticed they always did so in fixed, whole number ratios. It was as if they were discrete packets, pre-measured by nature. He revived the idea of the atom, proposing that each element was made of its own unique kind of indivisible particle. The universe, in this view, was a quiet assembly of solid atoms clicking together to form everything we see. This picture of a solid reality held for nearly a century. It was simple, it was intuitive, and it worked. But the first crack in this foundation appeared at the turn of the 20th century. In 1897, the physicist J.J. Thomson discovered the electron, a particle far smaller than any atom. Suddenly, the atom was no longer uncuttable. It had parts. The solid, indivisible sphere gave way to a new model, often called the plum pudding model, where negative electrons were scattered within a soft, positively charged body. This model, too, was destined for a short life. The true shift, the moment our perception of reality was altered, came in 1909, in a darkened laboratory at the University of Manchester. There, a physicist named Ernest Rutherford and his assistants were conducting a now famous experiment. Their setup was, in principle, quite simple. They were firing tiny, positively charged particles at an incredibly thin sheet of gold foil. Under the plum pudding model, they expected the particles to pass straight through, or be gently deflected. And for the most part, that's exactly what happened. Most of the particles passed through as if the foil were mostly empty space. But then, they observed something that, in Rutherford's own words, was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. About 1 in 8,000 of the particles didn't just pass through. They were deflected at large angles. Some even bounced almost straight back. Rutherford was stunned. The only way to explain this, he eventually concluded, was that the plum pudding model was wrong. The positive charge and almost all the mass of the atom had to be concentrated in an unbelievably tiny, dense core at the center, the nucleus. The vast majority of the atom, the space where the electrons moved, was nothing. It was empty space. Let that sink in for a moment. The solid matter we perceive is something of an illusion. The chair you are sitting on, your very bones, they are 99.9999999% empty space. The solid matter in every human on Earth, if stripped of this emptiness, would occupy a surprisingly small volume. This was a profound mystery. Our detective story, which began in search of the ultimate thing, had led us to a world built of almost nothing. The question was no longer just, what are things made of? But had become something far stranger. What is the nothing that everything is made of? For a time, science had a placeholder name for it, the vacuum. A passive, featureless stage. But this simple idea of an empty void was about to be replaced by a new theory, one so strange it would make the emptiness of the atom seem tame. Physics was about to look into the void itself, and what it would find there would change our understanding of reality. The true foundation, it seemed, was not the particles, but the supposed emptiness from which they arose. The quantum revolution and the living void. The early 20th century was a time of crisis in physics. Rutherford's atom was unstable according to the old rules. A new set of rules was needed to describe this strange new microscopic world. This new rulebook came to be known as quantum mechanics. And with it came an even more profound shift in perspective, one that is arguably one of the quietest and most significant revolutions in the history of science. It's called quantum field theory, or QFT. Quantum field theory proposed something extraordinary. It suggested that the most fundamental components of the universe are not particles at all. Particles, it turns out, are not the primary reality. They are merely temporary excitations, fleeting disturbances, in something far more fundamental: invisible entities called fields. Imagine the surface of a vast, calm lake stretching out to infinity. This is the field in its resting state. Now, if you toss a pebble into it, you create a ripple. That ripple travels across the surface. In quantum field theory, a particle is that ripple. The entire universe, in this view, is permeated by these fundamental fields: an electron field, a photon field, and so on. One for every type of particle we know. What we perceive as a particle is just a localized vibration in its field. You are not made of solid particles. You are a complex, coordinated dance of vibrating fields. A symphony of ripples on a cosmic ocean. But this leads to a deeper question. What happens when you take all the particles away? What is left when all the ripples die down? In classical physics, the answer would be simple: nothing. An empty void. But in quantum field theory, the answer is different. When you remove all the particles, the fields themselves remain. They are woven into the fabric of spacetime. What you are left with is all of the universe's fundamental fields in their lowest possible energy state. This is known as the quantum vacuum. And here is the quiet, mind-bending revelation of modern physics. This lowest possible energy state is not zero. To understand why, we have to invoke one of the bedrock principles of quantum mechanics: the Heisenberg uncertainty principle. It says there is a fundamental fuzziness to reality. One form of this principle states that you cannot know the exact energy of a system over a very short interval of time. This principle is the engine of the quantum vacuum. Because of this uncertainty, the energy in any given point of a field cannot be perfectly zero. It must constantly fluctuate. Even in its ground state, a quantum field is always shimmering with a minimum amount of energy, sometimes called zero-point energy. The quantum vacuum isn't a silent, static void. It is a seething, quiet hum of latent energy. And these energy fluctuations have a tangible consequence. If the energy at a point in space momentarily fluctuates high enough, it can borrow enough energy from the vacuum to create a particle-antiparticle pair, seemingly out of thin air. These are called virtual particles. They flash into existence, exist for a fleeting moment allowed by the uncertainty principle, and then annihilate each other, returning their energy to the vacuum. The empty space all around you is a constant, subtle flicker of these phantom particles. A vast, invisible ocean of potentiality. This is our deepest picture yet of nothing. It is not emptiness. It is not a void. It is one of the most dynamic places in the cosmos. Quantum field theory reveals the vacuum not as the background to reality, but as the very foundation of reality. This idea feels less like science and more like philosophy. But it is not a metaphor. The strange nature of the quantum vacuum is a core prediction of our most successful scientific theory. Its effects are real, they are measurable, and they shape the universe we inhabit in the most profound ways. The evidence for this seething emptiness is all around us, silently suggesting that one of the greatest powers in the universe lies in what we once called nothing. The power of nothingness. Evidence for the vacuum. The idea of empty space teeming with phantom particles is one of the most astonishing concepts in science. It's natural to be skeptical. But the quantum vacuum is not a philosophical abstraction. It is a physical reality, and its existence is confirmed by measurable evidence. The clues that reveal the power of this nothingness are woven into the fabric of the cosmos. Perhaps the most famous piece of evidence is a phenomenon known as the Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948. The thought experiment is simple. Imagine taking two perfectly flat, uncharged metal plates and placing them parallel to each other in a perfect vacuum, incredibly close together. Classically, nothing should happen. But the quantum vacuum changes everything. The vacuum is filled with virtual electromagnetic waves of all possible wavelengths. Outside the plates, this sea is unrestricted. But the space between the plates restricts which virtual waves can exist. Only waves whose wavelengths fit neatly into the tiny gap are allowed. This means there are fewer possible virtual particles inside the gap than there are outside it. The result is a slight imbalance. The vacuum outside the plates exerts more pressure than the more restricted vacuum inside. This creates a tiny, but very real, force that physically pushes the two plates together. This isn't a theoretical prediction anymore. This tiny force has been measured, and the results match the predictions with remarkable accuracy. The Casimir effect is tangible proof that the quantum vacuum is real and can exert physical force. But the influence of the vacuum isn't limited to the microscopic realm. In 1998, astronomers studying distant supernovae found that the expansion of the universe isn't slowing down. It's speeding up. Something is acting as a kind of anti-gravity, pushing spacetime itself apart. Scientists call this dark energy. While its true nature is one of the biggest unsolved mysteries in physics, the leading candidate is the energy of the quantum vacuum itself. The faint hum of quantum fluctuations, present everywhere in space, seems to be the engine driving the accelerating expansion of our universe. There is, however, a massive problem. When physicists try to calculate the theoretical energy of the vacuum, the number they get is 10 to the power of 120 times larger than what we observe. This discrepancy has been called the worst theoretical prediction in the history of physics. It tells us that while our understanding of the vacuum is profound, it is also profoundly incomplete. There is a deep connection between the quantum world and the cosmos that we have yet to fully decipher. The vacuum's influence doesn't stop there. An emerging field sometimes called polaritonic chemistry has shown that by placing molecules inside extremely tiny cavities, we can alter their chemical behavior. Confining a molecule changes the vacuum fluctuations it can interact with. This alters the molecule's energy levels and can change how it reacts. The vacuum itself becomes an active participant in chemistry. From pushing plates together, to driving the cosmos apart, to steering chemical reactions, the evidence is overwhelming. The quantum vacuum, this supposedly empty space, appears to be the active ground of our physical reality. This leads us to a quiet, staggering conclusion. If particles are just excitations of fields, and the vacuum is the ground state of those fields, then everything, every star, every planet, every living being, is, in a very real sense, a modification of the vacuum. Matter is not the primary substance of the universe. It is a ripple on the surface of this deeper reality. The foundation of everything isn't something solid, it's the boundless potential of emptiness. This journey from the ancient atom to the modern quantum vacuum is a testament to human curiosity. It's a story that continually unfolds, with each discovery revealing a universe far stranger and more wonderful than we could have imagined. If this kind of calm exploration into the world helps you unwind, consider subscribing. There are many more mysteries to explore together. We began with a simple question: what is the world made of? We followed a trail that led us from solid atoms to the vast emptiness within them. We journeyed deeper, into the quantum realm, and discovered this emptiness was not empty at all. We found a universe built not on things, but on invisible fields. And we learned that the ground state of these fields, the quantum vacuum, is a seething, energetic ocean of potential. The implications are almost too profound to grasp. It means the distinction between something and nothing begins to blur. Nothing is not a void, it is a structured and dynamic reality. Reality, at its most fundamental level, isn't static or material. It is dynamic and probabilistic. The universe isn't a collection of objects in space, it is the continuous, vibrant activity of space itself. We are left with a new and humbling picture of existence. We are not separate entities adrift in a passive void. We are part of the void's own intricate dance. We are patterns that have momentarily emerged from the quiet hum of the cosmos. And this revelation opens the door to even deeper questions. If the vacuum contains all of this potential, what are the ultimate rules that govern it? Why does it have the properties it does? Is our vacuum the only one possible? What caused the primordial vacuum to ripple in just the right way to create a universe, and us within it? The search for the foundation of reality has led us to the answer that the foundation isn't a solid floor, but an endless ocean of possibility. And as we stand on its shore, we realize the greatest journey of discovery is only just beginning.